now? Okay, cool. So, we have Monday, Wednesday, Friday. Today's Monday. Today we're going to talk about energetics. Wednesday is going to be chemical kinetics, and then Friday is something about acids, bases, and no, equilibrium, and then acids and bases. Okay, so we begin with writing. Oh, wow, I think I zoomed in a bit too much. Let me check the brush patterns. Okay. This is too thick. Let's go thinner. Okay, that's too zoomed in. Okay, there we go. So we have energetics. First, before we talk anything about energy related, we got to figure out what energy is. And that's a difficult question. So we're going to give a very hand-wavy answer, and hopefully it makes sense. So let's look at the kind of physics understanding of what energy is. So for people who took physics grade 11, this should be quite easy. And in physics, to first introduce the idea of having energy, we're going to introduce the idea of work. And in physics, work is defined as the following. Work is equal to force times the distance. But it's not just the distance, it's like if you have an object and you apply a force to it, and you're pushing this object, you multiply the force of you pushing in the direction that it's traveling in by the distance that the object traveled, and then you get work. And okay, let's look at an example of what that means, because that's confusing. And I have been trying to explain what work is in a simple for like many years now, and I still haven't figured it out. Maybe that's a me problem. Okay, suppose you're like some guy on a floor, and you have this box. And initially, this box is at rest, right? Box is not moving. You walk up, and then you push this box this direction. And then you push the box, say, you push the box 1 meter, and then you push the box with a force of, say, 3 newtons. You push with a force of 3 newtons, and then you keep pushing the box along 1 meter, all right? What's going to happen after this? And then you let go. After this, your box is going to continue sliding on the ground. We're going to assume that the ground has no motion. So our box is going to continue sliding forever. And let me try and draw that. So you push the box with 3 newtons for 1 meter. And okay, now the box is just moving forward, rolling along. Okay, does that make sense? I need nods or something. Okay. And we push the box with a force of 3 newtons by 1 meter. So according to this formula, we've been pushing the same direction that the box is moving. So we get that the work done by the person on the box is 3 times 1 meter, 3 newtons times 1 meter. Is equal to 3 joules. Joules is Newton times meter. We're going to say that this is our unit of work. Unit we measure work in, Newton times meter, which is called a joule. Okay, that doesn't matter. Now, we can talk about this like pushing boxes thing as like a person came along and pushed the boxes. But what if we're not interested in how exactly the boxes got pushed? What if we're only interested in like what it was before and what it was after in the end? And what it was before is a box at rest. And then we see, if we skip the part where the person pushes the box, we see that the box is moving at some speed v, right? So in essence, the box changed states. Before it was in a state of being at rest, and then it was in a state of like moving. Does that make sense to people? Yes, no? Okay. So we can see that we applied 3 joules of work to change the box's state from stationary to moving. All right? That makes sense. So the idea of energy is now, we can define energy as the following. A change in energy So I will define the change in energy, so definition, as the following. Change in energy, delta E, between two states, is the work required to go from one state to the other. This is a little bit of a convoluted definition, but once you understand it, I find it's very useful. One state to another. So, what does this mean? On the box example, initially the box is at rest. At the end, the box is moving, right? We can say that the change in energy from the box going from rest to moving is the work this person had to do to like push the box to that speed. All right, does that make sense? First times distance. Not too bad. Now in this case, when I mean state, I'm not referring to like gas or liquid, but like a general state of being, like box stationary versus box moving. Hopefully that makes sense. Now, we are not talking about physics. We're not interested in moving boxes. We're talking about chemistry. So the question is, what are the states of being that we are interested in chemistry? So let's look at the following examples. I'm gonna draw an arrow here. If you have any questions or anything is unclear, ask me immediately, because like I'm just gonna move on and keep talking forever, and you will, yeah, just ask straight away. So we have the following example. Suppose you have 4 atoms of hydrogen and it's in gaseous state, plus 2 atoms of oxygen, also in gaseous state. So you can just think of it, they're like some, okay, they're just like some dots, and they're like, stop. Wait, no, wait, okay. You have like some dots, this one's going here, another dot, this one's flying here. So these are like your 4 hydrogens, and then you have like 2 bigger oxygens. Okay, these are your oxygens, these are hydrogens, okay? This is their state of being, they're just flying around, right? Everyone agrees that this makes sense. Okay, now these same particles, these same atoms of hydrogen, they can be in the following state. They can be as 2H2 gas, where we have like a hydrogen molecule now. What are they called? Diatomic molecules. And a diatomic oxygen molecule. Yes. Do you agree? This is a different configuration of these same atoms, right? Yes? No? Makes sense? Nods? Okay. And the idea is, how do we go from here to here? It's a similar idea to the box. We take these atoms and we gotta push together, apply a force to push them together so that they bond, and like from 4 atoms of hydrogen, we push 2 pairs together to get 2 diatomic molecules of H2 gas, right? So it's kind of like small boxes, and you're pushing them together and you're sticking them together. So you still need to do some kind of work to go from this state to this other state. And you can think about it as like the force times the distance of you pushing the molecules together. Does that make sense? And we can define this, the energy difference between this state and this state. Sorry, the energy change going from this state to this state. Yes? Okay, I'm hoping that makes sense. And in this case, if you look at it, going from this state to this state, actually a better one would be, say, 2H, wait, it's 2H2, do I need 4? It's 2H2 I need. Yes, you can go from here to say 2H2O, right? Let's count, this is still the same number of molecules, because 4H2 and 2 O's, yes, correct. And this is, say, still gas, water gas, right? However, on one hand, this is like changing states of configuration of molecules, their kind of atoms, kind of state of being. At the same time, actually, am I recording? Yes, I am. Okay. At the same time, this is really just a chemical reaction of you going from like hydrogen and oxygen into water, right? Do you agree? Does this make sense? This is a chemical reaction, like this together. Yes? Okay. And now we've been able to define the change in energy for a chemical reaction, because the chemical reaction takes us from one state of like from one configuration of atoms to another one, and we reach this configuration by like pushing the atoms around and squishing them together. So we're doing some kind of work on them. So okay, we can now talk about the change in energy in a reaction going from one state to another. All right. And so that's a familiar configuration. We have water. Another thing that we can notice that it's not just about, you don't just have an energy change when you squish molecules together or push them apart or something like that, like we've seen so far. You can also have like a change of state in the sense of like liquid, gas, and whatnot, liquid, gas, and solid. So this is also, you need to do some kind of work to slow down the particles so they jiggle a little bit less, to go from gas to liquid. And all of these transformations are, well, this one's a physical, not a chemical one, but they all have some change in energy associated with them. So you can, the idea now is that energy is kind of the thing you need to go from one state to another. And I would like to note a couple things about going from one state to another. Say you have some configuration of atoms A, and then you have another configuration of atoms B. And suppose you're going from A to B, right? So say you're going from this one to this one, for example, right? And you have some associated energy change with that, delta E. If you were to go from B to A, the energy change going from B to A would be negative delta E. Does everyone agree with that? I'm not going to explain why that's true. It's just true. Trust me. Maybe don't trust me, but on this one, yes. So we push atoms together. I said that. Another thing is, suppose I know that doing this for two H2 atoms and an O2 atom to turn this into 2 molecules of water takes like, say, one joule. I'm just coming up with things. If I decided to do this same reaction but with double of everything, so I had 4 H2 gas plus 2 O2 gas to get 4 H2O gas, right? The energy change associated with this, because I have doubled how much of everything I have, is going to be 2 joules. So if you force more things to go from one state to another, then you need to use more energy, and it's like proportional. Okay, does that make sense so far, what I said? Yes? Okay. We will now pose the following question before us. Suppose you have, I'm going to do this in a very general way, so this might be vague if you, once again, ask questions if it's unclear. So suppose you have some kind of atoms. You're given some initial atoms. And initially, these atoms are in some configuration A. So A is like some collection of molecules that you've made out of these atoms or ions or whatever it is. And you have a chemical reaction where you go from A to B. You go from, I don't know, you go from, can I use this as an example? You go from these to these, for example. And then you have another configuration C. Okay? Suppose we want to find the energy difference, how much work we have to put into our molecules and atoms to go from A to B. Suppose this is unknown. Okay? So how can we find out what this energy change is? How can we find this out? AB. Well, you can set up a really expensive experiment to do this. But then it's going to be really expensive, and you're a student and you don't have money, so you're going to go broke because this is chemistry and you don't care enough to do experiments for it in your own free time. There must be an easier way. Well, suppose you didn't know what the energy is you need to get from A to B, but suppose you did know the energy you need to get from A to C and from C to B. So this is A to C. And this is the change in energy going from C to B. Okay? Well, it turns out you have this cool thing called Hess's law. And this is like 50% of the entire energetics unit. This very simple idea. The idea says the following. If you add up the changes in energy going from A to C and from C to B, that change in energy is going to be the exact same as just going straight from A to B. So Hess's law essentially says that energy-wise, the energy you use going from A to B is the same as going from A to C to B. And in essence, what this says is this diagram commutes. So you can like go along these lines. No, it is literally a vectors moment. Yeah, you add them to get places. And okay, this has been so far quite abstract. Actually, I'm not gonna give concrete examples just yet. Okay, and now the idea is the following. If you're given some like reaction going from A to B, right? And you don't know its enthalpy, and you want to compute its enthalpy, you have to find a bunch of other states, C, D, E, so A to B. You have to find some other states, C, D, E, F, whatever, such that you know what going from A to C is, from C to D is, from D to E is, and from E to B is, to find what going from A to B is. So if you don't know this one, but you do know all of these other ones, then you can just add them up, get how to go from A to B. Does that make sense? Not too confusing yet. It's a little bit confusing, but it should be okay. And that's the whole point of what you guys are going to be doing in energetics. You're going to be given some reaction, and you're going to also be given some like other information, like these others, A to C's, C to D's, and D to E's. And you're just going to have to pick out the correct states such that these form like a closed loop in a sense. So you can get from A to B, but using a different path. So regardless of the path you take through like your arrangements of molecules, you'll always get this. Okay, now we're going to move on to the next bit. So we're like continuing with this. We're just developing our idea. We're going to now change some terminology. Before I called delta E energy, change in energy between states, right? Energy between states. Between states. I said that going from one chemical state to another is literally a chemical reaction. So now we're going to now rename change in energy with enthalpy. This isn't quite the right way to do it, but you can think of change in energy associated to a reaction going from one state, one configuration of atoms to another, as the enthalpy, and we're going to call it now not delta E, but delta H. Okay? So now when I say enthalpy, I'm just saying the enthalpy of a reaction. So I don't know, what's a common reaction? NaCl plus NaOH, right? And then wait, is it NaOH? No, it's NaOH? Is it what's the thing?
HCl plus NaOH.
Oh, HCl? Right. It's NaOH plus HCl, right. I was thinking of something else. Wow, this is on video. People are gonna call me stupid 10 years down the line for not knowing basic things. And then it makes H2O plus NaCl, right? Okay. And then there's some states and whatnot. So the idea is, once again, so on this example, we have atoms Na, O, H, and Cl, and at first they're in this configuration, and then we move them around and like configure them in this way. And the enthalpy, and we notice that, so say this is state A and this is state B. Going from state A to state B is a chemical reaction, and with this chemical reaction, there's an associated enthalpy, change in energy, going that the work you need to put in to go from A to B, and that's delta H. Okay. This terminology clear. We're now calling change in energy as enthalpy and calling it delta H, right? Yes? Okay. Notice that enthalpy and all of these changes in energy are changes in energy. We're talking about the work we need to go from A to B. A itself doesn't have an energy, and B itself doesn't have like an energy associated with it. We can only talk about changes in energy, right? Yes. So now let's go back to the initial question of finding enthalpy of going from A to B. The idea is, like I said, we need to find other configurations of these atoms such that we know how to get from A to these other configurations. So we get a closed diagram like this to go from A to B. We go A to C to D to E. And so we essentially need to find a bunch of other suitable reactions, which if you like chain these reactions and do one after the other, you eventually start here and end up here in the end. And you need to make sure that you already know the enthalpy for these reactions. And in fact, in IB, you learn the following set of reactions. Let me find them here. I prepped a table for you guys, and actually this table it would be cool if I made a table like that when I was in grade 12, but I didn't care enough to try making tables for myself. I think it's page 3. Yes, okay, there we go. Here we have a pretty table of reactions. Wait, give me a second. I want to just move stuff around a little bit. How do I am boomer. Okay, like this. And actually, I'm going to make it a little bit bigger so it's better. Okay, there we go. Okay, and let's wait, I want to go back to the original layer. Okay, let's go like this. Okay, and we have the following reactions. These are the following types of reactions, which are generally useful as like intermediate steps for like going from A to B in some other path. And these are if you check your chemistry data booklet, there's like tables with enthalpies for all of these reactions for like different compounds. And it looks like it's a lot, but like once you look at their names, it's very easy to remember what they all mean. So this shouldn't be too bad. Let me move this layer down. And then we're going to look at some examples in a second. It's going to be helpful. So, okay, these are the types of reactions and their associated enthalpies that are generally known already, and you can use them to like find an extra path or whatever. Okay, first one is very simple, bond dissociation. Bond dissociation is if you have reactants and you break all of their bonds and you're just left with the atoms, right? And an example of that is you take water and you break all of its bonds. And there is an enthalpy associated with this. And we know what this, and for a lot of compounds, this enthalpy is known and you have it in a data booklet. So for example, if you wanted to find the enthalpy of this reaction just as an idea, what you could do, an intermediate step could be, you break all of this into individual atoms, plus O, plus H, plus H, plus Cl, and then you assemble this, but now in this configuration, so you could have this thing. And if you know the enthalpy of bond dissociation of this, right? And you know the enthalpy of bond dissociation of this. The enthalpy of bond dissociation of this is going in this direction, but you just take negative of that, right? And that way you can say, oh, if I know the enthalpy of how I get from here to the individual atoms and from the individual atoms to H2 and NaCl, then I just add this enthalpy and then add this enthalpy to get this total enthalpy. Does that make sense? As an idea of what you're doing? Yes, no? No, like some people are not nodding. Jocelyn, you're... Okay. So that's bond dissociation, quite simple. Just what is the energy we need to put into things to break all of the bonds? Energy of formation is a little bit more confusing. Energy of formation is, suppose you have a target product that you want to produce, say water. And this is the energy you need to put in to assemble this product from its constituent elements. But the elements are initially in their standard form. Actually, wait, I should fix this because this should be 2 and this should be 2, like this. Okay, I'm going to fix that later. The idea is what? We're making we're making molecules out of their elements. But initially these elements aren't in like their atomic individual form. They're in whatever they naturally exist in nature at like standard room temperature and pressure. So H2O liquid, you will form that out of the reaction of formation of H2O is the reaction of you going from H2 gas, because hydrogen is at room temperature just H. O2, because oxygen at room temperature is also a gas, and into water. There is like a list of things of what things are at room temperature, like if they're gaseous or something else, like Cl, chlorine, CO2, hydrogen. I think Br2 is also like a diatomic molecule that's a gas at standard temperature. But if you had something like Hg, like I don't know, HgCl, that's lead. No, not lead. What's the mercury? Right? Hg is mercury. Yes, no? I think it is. Well, if it's not, let's say Hg is mercury. Someone's about to say, okay, no. Let's say Hg is mercury, and what was I saying? And the equation for the formation of this would just be Hg liquid plus Cl2 gas, because at room temperature Hg is liquid and Cl2 is just gas. Okay, and this is a similar idea. I forgot to close this bracket. I should do that as well. This is in many ways with bond dissociation a similar idea where you can break everything into its elements, but not as atoms, as whatever they are in their natural state. And then if you know the energy of formation, the enthalpy of formation of this thing, then okay, you'd go like this, and then you'd go like that, and you add them up, and you'll find your overall enthalpy. Okay, I'll go a little bit faster with these because the rest are now a lot easier. Combustion, the enthalpy of combustion, that's just the reaction of you adding oxygen to something, and then you produce water, CO2, and then there's some energy or something released, so on and so forth. Vaporization, quite simple. Reactant turns from liquid to gas. Lattice enthalpy is not too bad either. You start off with an ionic solid like NaCl, and then you turn it into you break apart everything into individual ions. So you break up NaCl solid into Na plus gas and Cl minus gas, and always the gaseous state. So you talk about lattice enthalpy, you're talking about the enthalpy associated with this reaction, where everything turns into like gaseous ions. Okay, electron affinity is a reaction where the reactant that starts off in its gaseous state gains an electron. Ionization, you remove an electron, and actually, I think this is also in gaseous state. States are important because remember, going from gas to liquid to solid actually requires energy. So you have to make sure that your states all match up when you're setting up your like chain of equations. Okay, you have sublimation from gas straight to solid, fusion from solid to liquid, doesn't matter. And then there's hydration, where if you, I didn't find an example yesterday because I was kind of tired and didn't care. But hydration, if you remember last year, you guys did stuff like ligands or something, where you have like some ion and then you have some waters like attached to it and do something, but they're not like, it's like a dative bond or words like that. I don't know, it's very difficult words for me as a physics student. That's that enthalpy, and then I'll write in an example when I find one or you find one for me. Yes, so key thing to note, all of these things, all of these enthalpies are enthalpies associated to a specific reaction. This is something I find quite confusing in terms of the terminology. Oftentimes, always you refer to this enthalpy as like the enthalpy of formation enthalpy of H2O liquid. The key thing you have to understand that the enthalpy of formation or any of the other ones of these are not enthalpies that are associated with H2O liquid itself. It is the energy change associated with this reaction. Not just like it's enthalpy of formation of H2O is not some energy associated with H2O liquid. It is the energy change associated with going from this to this. So you have to really understand what the reaction is associated with with each of the enthalpies, rather than just know the name and that's it. Okay, now let's yes. Another thing, it says in the note here, these are the types of reactions, and all of the enthalpies associated with these types of reactions are called something like, bond dissociation enthalpy, enthalpy of formation, combustion enthalpy, vaporization enthalpy. With one exception, electron affinity is already the name of the enthalpy. Like, this reaction is not called electron affinity. It's the enthalpy associated to this reaction that's called electron affinity. I don't know why they did that cool naming school. It probably has some meaning, just not smart enough to understand. Okay, does this make sense? We're going to look at some examples right now in just a second. First of all, I want to really drive this idea of enthalpy of formation home, because I find it's one of the ones you use a little bit more often, I think. And if you understand this one, you understand the rest of them. So I'm going to give you the following reaction, and this is where we have the interactive part of the day. We have the following reaction. We go from H gas. Actually, yeah, no, sorry, that's a lie. I'm setting this up wrong. Okay, sorry. So question 1: what is the enthalpy of formation of H2 gas? Okay. So how do we answer this question? Well, we remember that the enthalpy of formation of H2 gas is the change in energy associated with some specific reaction. Do you agree? So probably to figure this question out, it would be useful to write down what this reaction actually is. Yes? Nods? No? Okay. So if I'm asking you what is the enthalpy of formation of H2 gas, you know that that's an enthalpy associated with some reaction. Let's write down this reaction. Okay, I'm going to open this chart again for you. Here's the enthalpy of formation, and please tell me what is the reaction associated with the formation of H2 gas. What is H2 made out of? What element is H2 gas made out of? So it should be a very simple question. And maybe someone will either say something or write in chat. Yes.
Hi.
Hi.
It's hydrogen. Wow.
Cool. And now we look at our cool chart, and our silly little chart says that we look at the elements that hydrogen gas is made out of, and then we put them in their standard state at room temperature and pressure. Okay, so what is the standard state of hydrogen at like STP, the standard form or whatever? Naturally, at room temperature, hydrogen is a blank. It says it right here for water. Naturally, hydrogen is something.
Gas. In the state of gas.
Just someone answer.
Huh? It's in a state of gas.
It's in a state of gas, and also it's not just gaseous molecules floating around, it's H2 molecules, like not just atoms, H2. So then what's the final reaction that we get? So we know for enthalpy of formation, our final product has to be H2 gas. For the specific enthalpy of formation, what's our reactant? Our only reactant, in fact.
H2 gas.
Exactly. H2 gas. Now, if you look very closely at this reaction, did anything happen at all? No, nothing happened at all. So what do you think the associated enthalpy of formation of H2 gas is? 0, exactly, because nothing happened. Okay. And similarly, if I asked you what the enthalpy of formation of O2 gas is, well, O2 naturally is just liquid. Oh, sorry, it's just a gas at room temperature. So yeah, this also has an enthalpy of formation of 0. Now, if I asked you what is my enthalpy of formation of OXO2 liquid, right? Well, what is the reactant to form O2 liquid for the enthalpy of formation, for the formation reaction? We make stuff out of everything in their atomic state, so you would make this in their, sorry, not atomic state, in like the thing where the elements are in their natural state at standard room temperature and pressure. Yes? I'm asking you for the reaction of formation of O2 liquid. Complete this reaction, and this is the reaction of forming O2 liquid. O2 gas, correct. O2 gas. And now, if I asked you for the enthalpy of formation of O2 liquid, that's the reaction of going from O2 gas to O2 liquid. But coincidentally, that is also the enthalpy of, what's the word? When you go from gas to liquid, it's the negative of vaporization enthalpy. So not from liquid to gas, but from gas to liquid. So that's one thing. Okay, I'm gonna do like 2 more examples. Let's see. Let's look at the enthalpy of formation. Oh, this is a useful one. Enthalpy of formation of, say, CH4. What is the enthalpy of formation of CH4? Well, first of all, what is CH4 made out of? What elements? Just say it out loud, somebody. Easy questions. Don't be shy. This has 2 letters, so there's 2 elements. Someone please say it.
Carbon and hydrogen.
Carbon and hydrogen. Okay, so we have carbon and hydrogen something. The following question is, what is carbon at room temperature and standard pressure, and how does hydrogen look like at standard room temperature and pressure? Hydrogen, we already know, is, we've said this like 10 times.
Gas.
Yes, but what kind of gas?
H2 gas.
Yes, H2 gas at standard room temperature and pressure. Hydrogen always like sticks together in pairs. We didn't talk about carbon yet, but I think carbon is just like carbon on its own. And okay, carbon is just like, I think, solid. Okay, and this is, I don't care, whatever, liquid. But this would be the reaction of formation of CH4 liquid, of you going from this to this. Okay, now that we've figured out this, let's look at a more concrete example. This is the one that I've gracefully stolen from of something. Computer Breakdown Live, that's great. Okay, let me make this a little bit smaller because my handwriting always starts getting bigger and bigger as we progress. Okay, so far no one has any questions. So the idea is we are trying to find a method to compute enthalpies for reactions, and we've just come up with like simpler reactions that we can use as steps to like circumvent the actual reaction, and then we add up enthalpies and go and use Hess's law to make our computation. Okay.
Oh, sorry.
We're gonna, yeah.
For like the question that you wrote originally is what is the enthalpy of formation of, you know, like whatever element
Yes.
you're doing. So when we're writing the equations, oh wait. Were we just practicing like writing out the equations and not actually finding the enthalpy?
Yes, we're just practicing figuring out if I'm saying the enthalpy of formation of something. That means it's the enthalpy associated to some reaction, right? And it's important to understand what this reaction actually is.
Okay.
Given like whatever compound, if you have CH4, how do we figure out what this enthalpy is? Now, enthalpies of formation are something that is generally well known. Like people have done lots of experiments, and once again, your data booklet has like entire tables of this. Actually, key thing that's like a trick in your data booklet. It's a trick. They're trying to trick you. For like lattice enthalpies and I think ionization enthalpies, in your data booklet, it's like separately called, like there's a separate chapter called like lattice enthalpies table. But then for the enthalpy of formation, which is the one that at least I've always used most often, for one reason or another, the table where that's in is called selected compounds thermodynamic data, just so that it's more difficult for you to find it. So that's something to watch out. Like you should at least once in your life check where these tables are, because on the test, flipping through that data booklet without having Control F available to you is annoying. But even with Control F, I don't think they even have the word formation. They just have like the delta HF symbol. So that, like IB is just trying to screw you over for no reason. Can't even make titles that make life easy. Okay. So now let's compute. I'm going to ask you to do the following. We have the following reaction. We have 2NO2 plus O2 gas plus turns into 2NO2 gas. Okay. And I'm going to ask you to, we're going to right now compute the enthalpy of this enthalpy of this reaction, okay, using enthalpies of formation. So when I say enthalpies of formation, the idea is going to this. We're going to take the reactants, break them into their like standard, into their elements in their standard state at STP, and then we're going to, from those elements, put them back together into NO2. All right. So, can someone please tell me the reactions of formation of NO and the reaction of formation of O2 gas. Well, this one we've already done, but let's start with NO. So we want to make NO. What are we for a reaction of formation? What are we making NO from for formation? We just did this thing. Like it's the same type of question as we had just for CH4 and so on and so on.
Nitrogen and oxygen.
Nitrogen and oxygen, but in what states? So oxygen is always
O2.
O2 gas at standard temperature and pressure. Nitrogen, there's a lot of it in our atmosphere. So at standard room temperature and pressure, it probably is
A gas.
a gas. And it's also, if you remember, Hofbrinkel. Hofbrinkel is all the stuff that you remember is diatomic. You remember it's all the stuff that's diatomic at standard room temperature and pressure. Hofbrinkel, so that's N. So you know that that's a 2 as well. Now O2 gas, what do we form O2 gas out of? According to our definition of a formation reaction, it is made out of, someone say it. Just
O2.
O2 what?
Gas.
Gas. Okay. So now we know that, and I'm going to now tell you from the website. The website says that this. Oh wait, actually, this is 2NO. That this is delta H, the enthalpy of formation of NO2 of O gas is 90.25 kilojoules per mole of NO. This is something I kind of skipped. What this means per mole of NO means that to produce 1 mole, 1 unit of NO, we out of this we need 90.25 kilojoules. That's all that means. That to produce 1 mole of these. Remember, moles are just like counting molecules in dozens, but they're very big dozens, very, very big dozens. Okay, so now we get the following, and what's the enthalpy associated with the formation of O2 gas? We just said that it is anything happening in this reaction? Does there have to be? No. So the enthalpy of formation of O2 gas is 0. Okay, cool. So now we get the following reaction. We get that N2 gas plus O2 gas plus more O2 gas gives us 2NO plus O2 gas, and the enthalpy associated with this reaction, so H1 is equal to 90.25 kilojoules per mole of NO2 produced. Kilojoules per mole of NO2 produced. Mole of mole of just NO, of NO. Yeah, I think that's what it is. Okay, that's one thing. Now let's look at the enthalpy of formation of our products, right? Can someone please write down for me? We want to produce this. What is the enthalpy of, what is the reaction associated to the formation of NO2 for elemental things? What elements do I have in NO2? What elements? 2 of them, 2 letters.
Nitrogen and oxygen.
Cool, nitrogen plus oxygen. Now, at room temperature, how does nitrogen and oxygen look like? They are Hofbrinkel, and they're gas. So they're gas, and there are 2's on them. And so this is the formation of 2NO2. Okay. Actually, wait. I need. Give me a second. Let me figure this out. 2NO2, 2O2. I need 2 of these. Okay, see how this is all fitting nicely. So we have these two equations, right? And if you notice, so this is equation 1, this is equation 2, and actually this I will tell you has an enthalpy of 33. H2 has an enthalpy of 33.18 kilojoules. Whoops, let me erase this. 18 kilojoules per mole of NO2 gas, I think. Yes, because this is gas. Okay, cool. And these numbers are just numbers you look up in the data booklet. Actually, the numbers for these specific reactions I don't think are in your data booklet, but who cares? Okay. So now if you notice, this side is the same as this side. This side is the products in our original reaction, and this side is the reactants. All right, so let's draw a diagram that might be a little bit easier to understand. So our initial reaction was what? We had 2NO plus O2 gas. I should zoom in a little bit. Plus O2 gas, and then we had our final state is 2NO2 gas. Okay. And we also said that we know how to get, so we don't know how to get from this state to this state. We don't know. That's what we're trying to find out. However, we do know how to get from, sorry, I'm doing something. Yes, how to get from N2 plus 2O2. N2 gas plus 2O2 gas. We know how to get from here to here. Do you agree? Because this is the enthalpy, this reaction forward, this is the enthalpy of formation of NO and O2. Do you agree? This is the reaction of forming these two out of the elements. Does this make sense? So going from here to here has enthalpy H1, which we said is like 90.25 per mole of N2. But going from here to here is the enthalpy of formation of NO2, and we also know that, right? We also wrote down the reactions for that, and we also know that. And this is delta H2. And if we want to find delta H, we have to go along this diagram like this and add stuff up in this direction. Do you agree? Does this make sense? To find delta H, we have to go along this direction and add stuff. Now, one thing we have to notice and keep in mind, that first of all, hey, delta H1 is us going from here to here, but we want to go the other way. Do you agree? We want to go backwards. So the enthalpy for going backwards like this is negative delta H1. All right? Yes? No? Perhaps? This makes sense? Okay. So then our total enthalpy going along this diagram is the fact that, hey, we first go to our like elemental states and we do negative delta H1, and then we add delta H2, and then we're done. And so you would just add these up like this. Does this make sense? As an idea of what we're doing. So here is an example of what I said is we found an alternate route to get from here to here for which we know the enthalpies, right? We didn't know the enthalpy for this, but we knew the enthalpies for going here and going there. So we found this other alternative route and added it together to find the energy of going from here to here directly. Okay. However, there's a small caveat of how I gave you the enthalpies. This isn't it. Remember I said everything about the whole moles thing of a per mole of NO, right? Here we use up 90.25 kilojoules per making 1 mole of NO. Oh, yes, high questions.
Yeah, so like the numbers that you got, are they just from like a data book or something? Like
yeah, you just find that in a data booklet. These are from a website. I copied off. For the reasons of this demonstration, I could literally like write 1, 2, 3, and it doesn't matter. The age is the same, but yeah, you'd find them in a data booklet. The whole point of why I'm asking you to write out all of these reactions, like what does the reaction of formation look like, is that in your data booklet, they just say, oh, this is the enthalpy of formation of this element, and they don't tell you what the reaction actually is. But as you can see, to figure out like how exactly if all of your coefficients match up and you're making everything in the right proportions, you need to like know how to make the reaction yourself. But then the data booklet doesn't give you that. So that's kind of the difficult part. Then adding numbers is you have a calculator for that. But yes, a good question. Wait, sorry, I want to move this to the side because this is in my face. Okay. Okay. So the idea, oh no, I've been writing on the wrong layer this entire time. Okay, that sucks. Well, the idea, what was I saying? Yeah. So here I said delta H1, this is kilojoules per mole of NO. So for 1 unit of NO you produce, you make 90.25 kilojoules. But here we produce 2 moles of NO, right? So here we made 2 moles of NO. So we need to multiply this by 2, actually. We need to multiply this by 2. And then our enthalpy number 2 is we're making 2 moles of NO2. And this is per 1 mole of NO2. We're making 2 units of NO2. So we have to multiply this by 2. Oh. Does it make sense why we're multiplying? Because we have to match up the quantities of the stuff we create and the stuff we use. Right? Here we've used 2 moles of NO to make 2 units of NO2, right? If we used 1 unit of NO and made 1 unit of NO2, then we don't need to multiply anything. But here we've just doubled everything. We've doubled the quantity of the stuff we're producing and the stuff we're using to produce it. So we have to double all of these enthalpies. And this is one of the key things that you have to watch out for, that the enthalpies are like always per mole of a reactant or a product. And notice that at the end, this reaction is going to be enthalpies in kilojoules per mole of NO2, I think, of NO2 gas. It's per mole of NO2 gas that we use, or per mole of NO that we use up here. And if you compute this number, this is going to be -2 times 90.25 plus 2 times 33.18. And the website said that this is negative 114.1 kilojoules per mole of O2. No, wait, of O2? No, not O2. This to be, I think, yeah, this has to be of NO. Whoops, my bad. I should fix this. I think it's NO. Let me double check this. Of N2 or NO. Yeah, it's NO because, let me think. Yes, should be NO. So we're good. Actually, in a sense, in a sense, I kind of lied to you, because the enthalpy of formation of a single molecule of NO, whoops, wrong layer. The enthalpy of formation of a single molecule of NO, it's always per mole of NO, would be 1/2 molecules of this plus O2 gas, like that. And in this case, you can put a 1/2 in front of a single like bit, because 1/2 refers to like if you have a bunch of atoms of N2 gas, like not just a single atom, but a lot of them, we need 1/2 of a mole of N2 plus a mole of O2 to get 1 mole of NO2. So actually, all of this should ideally be halved like this, but and that's why you have to multiply things by 2, because to get yeah, sorry, this is the, let me write down the correct reactions for the formation of Formation is always to make one single molecule. So this is 1/2, this is 1/2. Do you agree? And in this case, because we want to produce 2 molecules of N2, we're going to have to multiply this entire equation by 2, and then the enthalpy would then be 90.25 and not 90.25 times 2 and not the other way around. Okay, I set this up in a little bit of a confusing way. Does it make sense why we multiply things by 2 and why these things are halved? Jocelyn, questions? Don't just nod if you actually have questions.
You know the equation that's like the really long one, the N2 gas plus O2 gas plus O2 gas, that one?
Yes.
Yeah.
Yes.
It's all halved, right?
Not all of it. Good question. Not all of it. This equation is we took this equation and put it together with this equation. Do you agree? So actually, you're right. It is. You can you have this, and then you have this, but this and this comes from its own separate equation. But actually, you're right. You would want to have that as well, because we want to. Hold up. I'll show why. 1/2, 1/2. You want to have that because you want to produce. You want to go from. You want to produce 2 NO, right, and 1 O2. So you want to halve the O2 as well. But this part of the equation is its own equation of formation. I just added these 2 equations together. I said let's do these 2 things at the same time, and technically you need to have each equation on its own, but in this case we want to have everything because our final product we want to be 2 NO and 1 O2. So you want to have the O2 as well, so you're not left with 2 O2. We don't need excess O2 gas. Okay. So you'd have this like this. You'd get 1 NO plus 1/2 O2, and this has enthalpy H1. And then you'd have this second equation, enthalpy whatever. But then your equation that you want to know is 2 NO plus O2. And this tells us of us going from half N2 plus O2. So we need to double the quantity of everything to match up the numbers that we had in the original equation for which we were asked to compute the enthalpy, which is why we multiplied all the enthalpies by 2, because we just doubled the quantity of the stuff that we are making.
Okay.
Okay?
Thank you.
That shouldn't be too bad. Okay, so I messed that up. Let's see how many more things I'm going to mess. And now we're going to move on to our 3rd example. And then I think we might take, oh, yes, hi.
Sorry, I have a question about what Jocelyn said. So for the, sorry, normally you just want the final product of the enthalpy of formation to be 1 mole, and is it but this for Joss, the equation that Jocelyn was asking about, in the end it had 1.5 moles, right? So
yes.
Is it just because it's a sum of the 2 previous
equations? Yes, I took this equation. So look, I want to find an equation of going from this side to somewhere else and then back to here, right? And I found an equation of how to dissect this into elements. Sorry, I found an equation for how to dissect this into elements and this into elements. But I don't want to find the individual equations. I want to find an equation for how to dissect both of these things into elements all at once, right? But dissecting one thing into elements and then the second thing into elements is still dissecting the entire thing into elements. So I just wrote them together as one thing. Even though 2 separate things are happening, I'm splitting this into its elements first and then this into its elements first. But I just think of it as I'm doing this one thing and splitting both NO and O2, all of the reactants together in elements. And that's why I write this equation. Okay. I'm gonna give you a moment to think about while I check the 5 emails that I've received in the last 10 minutes. Wait, what? You got
Could you put the thing on the table that you created so I can copy it down?
the table? This? I'll send the table to you guys, don't worry about it.
Okay, thanks.
Oh wait, no way. I got Mark's. Okay, don't worry about it. You were, Eileen, are you saying something to me or someone else? Oh, Jocelyn?
Oh, I was gonna say mark reveal, but that doesn't
Oh.
seem like a good idea.
Mark reveal. Oh, no. I just asked for like, I was confused as to, on like 2 of my homeworks, I was confused by what the TA commented, and I was like, what the TA is saying is just, I don't know what they're saying. And then the prof was like, well, I don't know what they're saying either. I think you're right.
Did you mix up me and Jocelyn? That's pretty unslave you.
Unslave me for what?
For mixing
Oh.
up me and Jocelyn.
Yeah.
I didn't mix you up. No, Eileen, you were saying something. Like it looked like you were saying, I was like, oh, are you boomer? Forgot that you're muted? 'Cause that happens with you. That happens with you more often than it does with me for some reason.
That is not true. That is so untrue. Okay, I was just talking to Lindsay.
Okay, guys, this is recorded. Remember this. We'll talk about it later during break. All right. Also, I probably don't want to know what you guys were talking about. Okay. I was numbering this in some way. 1, 2, 3, 4, 5. Okay. We move on to our next example. And the next example is a little bit confusing. But once you understand the point of it, it becomes trivial, like all of chemistry and all of science. Completely obvious. Nothing difficult. Why is it obvious? Because someone has thought of it before. Wow, I have so many typos in my in the stuff I wrote. Okay, you're given the following reaction. It's a weird reaction. Plus Cl minus gaseous. This is NaCl, I think. Okay. If you have a really good memory, and you're given this reaction, and I'm asking you to find the enthalpy for this reaction. Now, if you notice, this is the reaction associated with the what's it called? This is the lattice enthalpy of NaCl. This reaction is the lattice react NaCl. However, oftentimes, like this is a difficult experiment to do, and let's try and like come up with other, like find another way using all of these other reactions to get the lattice one. So like, let's find other reactions that we can go to find the lattice reaction. Does that make sense what I said? So find a way to get from NaCl solid to Na plus gas plus Cl minus gas, but not just by going directly, but by going in some like having some other steps. Okay, kind of like what we did before. Now, one thing you can notice straight away is here you have ions and stuff. So it's not as simple as just using enthalpy of formation. But okay, how do we solve this kind of question? How do we figure this out? How do we find the steps of like what are the alternative route that you go to get back to Na plus gas to Cl minus gas? Okay, well it's quite simple. You just have to look at the differences between the right-hand side of the equation and the left-hand side of the equation. So guys, just start listing stuff for me. What's different between this and what's different between this? One thing at a time.
One is solid, the other is gas.
Okay, cool. One is solid, the other is gas. That's one thing. What's another thing?
One is neutrally charged and the other is two ions with charges.
Yes. So, oh, I got some lemon. Okay. The idea, that's good, but I'd say there's three things. This one, Na and Cl are together. This one, Na and Cl are separated. That's one thing. So when we make our path, we're going to need to have a reaction that one separates Na from Cl. Na from Cl. Casey pointed out that we have to also turn them into gas. At some point. And then, sorry, that was Iris. Iris said that, well, we want to ionize, we want to like turn them into ions. Turn Na and Cl into ions. Well, okay. So we just need to come up with a bunch of reactions from the ones in the table that will do all of these things. Okay? And we're just going to draw a diagram. So let's start with NaCl. Solid. Okay. Let's do the first thing. Let's separate Na from Cl. What's something that takes Na and Cl and puts it into its like elements? We just talked about it. The reaction of starts with an F.
Formation?
Exactly. So, okay, what's the reaction of formation? What's the reaction of formation for NaCl? What is Na at standard room temperature and what other things? Someone please answer. And Na and Cl. We've done this a few times. But like, don't worry. This is not the easiest and most intuitive of things. So if you need a bit of time to think, that's okay. What is the reaction of formation for NaCl? Just say something.
It's Na solid.
Okay. Plus?
And then was Cl one of the? I don't think so. Right?
Well, what's the acronym?
Was Slay. Love that. Okay, so it's Cl2 gas.
Cl2 gas. Okay. Cool. And we know the this enthalpy. This is the enthalpy of formation of NaCl. And that's good. Also notice that this is all fine because we're producing only one molecule of NaCl, so we don't have to scale this by anything. All right? Makes sense. Now, we've separated Na from Cl. We now have to look at this equation and see what's different between this equation and the final product. What do we still have to do? One of the things is we need to turn this into gas, right? And we need to ionize both things. But one of the thing I want to deal with first is notice this is Cl2 and that's Cl. Oh wait, sorry, this has to be 1/2 of Cl2. I'm sorry, 1/2 of Cl2. And this is just Cl. Do you agree? How do we turn Cl2 into Cl? What do we need to do? What does Cl2 look like? Cl2 is like a thing, and then you have another thing bonded to it, tethered with something. What do we need to do to just get Cl on its own? We have to, wait, can I, what do you have to do? You gotta cut the rope, right? Scissors. You cut the rope. And you have to break this bond. Yes, make sense? Does it make sense why we want to go from Cl2 gas to just individual Cls? Yes, okay. So this is what kind of enthalpy. I'm gonna show the chart and you guys are gonna tell me. This is the what kind of reaction it is for Cl2.
Bond dissociation?
Yes, it's bond dissociation. The reaction is bond dissociation. The enthalpy is often referred to as bond enthalpy. Okay, so now what we're going to do is bond dissociation
Wait,
of Cl2.
I think I
And
missed something.
sorry, you were saying?
Sorry, I think I missed something. Why are we? Is the half of the Cl2 part of the equation?
Yes. Why? Because we said that we want to create 1 mole of Cl, of NaCl, from Na and Cl2. But
Okay.
Na and Cl has 1 Na, 1 Cl. And Na, okay, we have 1 Na, but Cl2 has 2 Cls, so we got to multiply it by half.
I understand
Okay.
now.
Now we are dissociating Cl2, right? And we want to get, so the NaS, we don't do anything to the NaS, so I just carry it over. And now we want to dissociate the bonds of Cl2, and because we have half of them, we get Cl. However, because we're dissociating only half of bonds of Cl2, right? The enthalpy for the bond dissociation of Cl2 tells you how much energy do I need to put in to break the bonds of a single Cl2. So breaking the bonds of half of a Cl2 is going to be 1/2 of the enthalpy of bond dissociation of Cl2. Band director of Cl2. That was not funny. You should not laugh. Shame on you for laughing at an unfunny joke. Okay, now what we have looks kind of like what we want it to look like. We have Na and Cl gas, right? So we have a separate Na and a separate Cl. What do we have left that's different? This one is solid. That one's a gas. This one's a gas, so that's good. And then there are also ions, right? So what are the steps that we have left to do? I'll write this out. What our target thing is. This is our target. This is our target. What is it that we have left to do to this to get here? Give me a single step. Somebody, please. Think about it. What do we got to change about this to make it look like that?
A single thing.
Just give me one thing. We're going to do one thing at a time.
Like what? That one.
Charges?
Charges, okay, but one thing at a time. Charges is a vague answer. Change the charge of this thing to this charge.
Oh,
Or be specific.
make the
Ionization of each one?
Pardon?
One is ionization, the other one is, what was it called? The electron something? Affinity? Affinity, yeah.
Yeah, sorry. So you're saying we should change the charge of what to what?
That's referred first to like sodium with like electron affinity.
Okay, yes. Of which element? Just choose one. There's 2 of them. Just say a word. Just Na or Cl. Sodium. Okay. So you're saying this is ionization energy actually, because we're taking away is ionization, electron affinity is giving one. So okay, fair point. Let's take away a single electron from Na. We go back to our chart. Remember, this Na is solid. We go back to our chart. We look at the ionization energy, but oh wait, the ionization energy is remove an electron from a reactant in gaseous form, right? Can we apply the ionization reaction to Na just yet? No. So what do we have to do first?
we have to make the Na into a gas.
Exactly. And if you look at this chart, which thing does solids and gases? It's closer to the bottom.
Negative sublimation.
Negative of sublimation, exactly. Sublimation is from gas to solid. We want to go from solid to gas, so we're going to do the negative of sublimation. Okay. So I am going to actually write it, so Na gas plus Cl gas. And I'm going to draw the arrow this way because originally the reaction of sublimation of Na goes from here to here. Do we have to multiply anything by 1/2 or anything like that? No, because we took 1A, 1 Na, and we got 1 Na back. Perfectly fine. Okay. And now, Lindsay, you were saying that we want to do something to Na, which is we wanted to give it or take away an electron. Lindsay, answer.
Take that away.
Take one away. We want to take away an electron from Na, and we do that using the which one is it? The ionization energy of Na gas. Okay, so we have this A delta H ionization Na, and this gives us Na plus in gaseous form plus Cl in gaseous form. Okay, so what do we have left? We want to make stuff look like this. What is the one thing we're missing? We need to, what's the one difference?
Add an electron to Cl.
Okay, and adding an electron, we go back to our chart. Known reactions for which we know enthalpy, it is?
Electron affinity.
Electron affinity, perfect. So this is the electron affinity reaction. So delta H electron affinity, it's actually confusing, but that's fine. Electron affinity of Cl gas, and then we get Na plus Cl minus gas. Okay, and now if we want to find the overall enthalpy for this reaction delta H, gotta add everything in the with the right signs. Okay, so let's just go in order. First thing, do we add HF NaCl or do we subtract HF NaCl? Because remember, we're going like this way.
Subtract.
Subtract, because this is the energy like going backwards. We want to go forwards. So delta HF NaCl. So this is delta HF NaCl. Then we have the bond dissociation of Cl2. This is in the right direction. So, and we already, this is the key thing. It's always good that when you're making this kind of diagram, write in the 1/2 straight away, because otherwise, like if you try and add in the halves later, you'll just get confused. So, okay, then we do plus 1/2 of the enthalpy of bond dissociation of Cl2. Very nice. Then we did what? Then we went from here to here, but we're going, this gives us the thing backwards. So we want to make it negative. So subtract the enthalpy of sublimation of Na. And then we want to add the energy of ionization of Na. And then the enthalpy of the electron affinity of Cl. And then you would have all of these numbers from your textbook, and then you just add all of these numbers up, and you'd have your answer. Do you agree?
I agree.
Does this process of what we did make sense? We didn't know this enthalpy, so instead of finding this enthalpy, we found like a bunch of other steps to get from here to here in like a different path. And we knew the enthalpy for these, or at least we pretend we know, and then we just add all of them up. Now, the way I formatted this diagram is, while intuitive, is not the canonical way to do it. I think this is called actually like the Born-Haber cycle, because that's the stuff for like lattice enthalpies and things. This has a specific name. you will learn its name at some point, but in reality, this is just a cool application of Hess's law. So far, all we've done for like the last hour is just applying the fact that, hey, if you go from A to B, that's the same as going from A to C and then C to B. That's all we've done for an entire hour. Like the first month of chemistry is like this diagram, and that's it. There's nothing more to like the first month of chemistry. It's just this diagram, nothing else. Some people say like this is difficult. No, it's like a triangle. A triangle or a circle that's like half of high school. It's either a triangle or a circle, and it's obvious. Now, what was I saying? The difficult thing is, well, for me, the difficult thing is this diagram is supposed to be formatted in a specific way, where you write these reactions as like a ladder of some sort, where you draw them like, okay, you start at this NaCl solid, and then you go up, and then it's what did we do? We did Na plus Cl2 gas, and then this is 1/2. Actually, our arrow was pointed this direction, and we had some like delta H1 here, and then we went up here, and then we did Na solid plus Cl gas, and then you go up again. I'm probably drawing this terribly wrong, but I'm getting like the shape of it correct, more or less, I think. Cl gas, and then you go up again, and you make it Na plus gas plus Cl gas, and then, okay, I don't have more room to go up, but you'd go up again, and it'd be Na plus gas plus Cl minus gas, and then this, the reaction going from this bottom thing up top is the reaction that we wanted to have, but we found like other steps to get up there. Yeah, that's it. That's the point of this.
Wait.
The only difference is like I just redrew what I did here, but in a neater way, and this is going to be the way you're supposed to do it for tests and things. You'll figure it out. Whoever your teacher is going to show it to you, and you'll memorize how to draw it properly. But the idea between this diagram and this diagram are the same. It's just a notational difference. Okay. So this concludes kind of the Hess's law part of the energetics unit. Do people want to take like a 10-15 minute break? Make more lemon tea? Then we'll continue with other stuff. Or do people have to go or something? I think the other part is going to be also like 1.5 hours-ish. And then we'll be done. The other part is even easier than this.
Could you clarify why we had 1/2 of Cl2?
Of Cl2, yes, that's one. Yes, this is a good question. This is an important question. If you look here, we are making 1 unit of NaCl. Do you agree?
Mm-hmm.
And the reaction of formation demands that we make this 1 unit of NaCl out of Na solid and Cl2 gas. We have to use Na and Cl2 to make our NaCl. That's because we know only for formation.
Is that why we make like we take a half of we take a half of Cl2
to mass balance? So we have the same number of Cls in here as we do in here.
Oh, is that the same reason why we did that with the previous question with the?
Yes, it's always the same reason. You want, because remember, like if you convert more stuff or less stuff, that changes how much energy you use. And we want to get exactly as much energy as we need to make 1 thing of NaCl. We want it to match up exactly. If I had 1 Cl2, if I had Na plus Cl2, well, this would be giving me NaCl, and there's going to be another Cl left over. I don't want that. I want to have exactly NaCl. And this is what the energy of formation describes. The energy of formation describes as a reaction where you make exactly 1 unit of NaCl out of Na and Cl2. So it's this reaction. And on one hand, like you've learned, hey, you can't have like halves or coefficients. But here we aren't talking about individual molecules. Here we are talking about like millions of molecules, and then you just take half of them, because we're talking about like in moles. And you can always like half energy and things like that. So that's fine.
Okay.
We aren't talking about molecules like in general quantity of things.
Okay, all right, yeah. I
Okay,
understand.
any other questions?
Just to make sure. Oh, Oh, sorry.
So no, I was gonna ask questions.
Oh, okay. Just before, but the enthalpies that you take, like the delta H and whatever, that's you're taking the enthalpy of whatever you're changing, right? Like, for
Yes, yes. Like I'm taking the enthalpy of the reaction that I'm doing to get from one step to the other. So here, so for example, going from, actually, this diagram is a lot neater. So for example, here, I did what? I changed Cl2 bond, and I broke the bonds in the Cl2, right? I didn't do anything to the Na. I didn't touch the Na, right?
Right.
So since I only broke the bonds of Cl2, then this reaction is me breaking bonds of Cl2. So it's the enthalpy of the reaction of me breaking the Cl2 bonds. So the bond dissociation of Cl2.
So if you change both of them,
Then you're going to add the enthalpies. You should always think, that's why you should do things one step at a time. You change one thing at a time.
got it.
You could change both of them, but that's the same as just like adding the two enthalpies together, because you're doing two separate things at the same time. Now, actually, just a fun remark is I legit don't know how they in reality do any of this. Like, I don't think it's physically possible for them to have Na and Cl mixed together and they manage to like only ionize the Cl and not the Na. So in reality, you will never really have this happen, as you will never have like Na and 1/2 Cl2 gas sitting in one bowl together, and then they somehow magically don't touch the Na but do stuff to the Cl. However, by Hess's law, it still says that the like overall energy changes are still fine and all the same. Okay.
Kind of unrelated question, but how do they like what experiment do they do to
That's a
determine-
great question. No idea. Zero idea how they do it. No clue. Maybe for electron affinity, I can imagine like electron affinity, they just take the thing and like shoot electrons at it or something like that. For combustion, okay, for combustion makes sense. They just react it. Yeah, we are going to talk about how to actually measure these enthalpies in like the next bit. Okay, any more questions? Like, does that kind of answer your question? Because like, I honestly don't know, like, how do you take H2O? Like, how do you take hydrogen and oxygen and you just take it in an H2O? There's probably some way to do it. It's just like weird and confusing, or it's something.
Could you actually send that like chart?
I'm going to correct the chart and I'm going to send it later.
Okay. All right. Thank you so much.
All right. I'm also going to send everything I annotate here. Okay, we're back for second half. All right. So we've just introduced this idea of changes in energy going from one state to another. And we've applied it to chemistry by saying, okay, hey, atoms can be arranged in this way, and then we can arrange them in this different way. And going from one state to another, like that is a chemical reaction, and therefore there's an energy change associated with this reaction that we now call the enthalpy of that reaction. Cool. Then we said, hey, we have this cool fact, which is Hess's law, which is just true, because just trust me, that if you go from state A to C and from state C to B, that's energetically the same as going directly from A to B. Okay, and that's cool. So now, if we don't know the enthalpy of going from A to B, but we know the enthalpy of going from A to C and from C to B, we can now add the enthalpy going from A to C and C to B to get the enthalpy of going from A to B. Okay, and we've just seen that for 1.5 hours with a lot of examples. The question is, what if we don't have this like magical step C, which helps us solve all the other things? What if we don't have a step C such that we know what the enthalpy of going A to C and C to B is? Well, in that case, like I said, we can set up a really cool experiment. And the question is, how do we set these experiments up? How do we experimentally determine the enthalpy of a reaction? All right, that's our next question for the next 1.5 hours that we're going to explore in detail, right? So we came up with a theory of it. Now, how do we experimentally do this? Does this question make sense? Why we're asking this question? Wait, hold up, sorry. Okay, yes, sorry, I didn't see nods. Does it make sense why we're asking this question? Okay, cool. So question. How do we experimentally determine the enthalpy of a reaction? The enthalpy of a reaction. And the thing I want to say about this is that here we're assuming that we know how to physically do the reaction. When Iris, I think, asked me like, hey, how do they do these experiments for, say, like the lattice enthalpy? Like, I don't know how they physically do the reaction. But if I did know how to do the reaction, then we can like come up with an experiment in kind of the following fashion. And in high school, we learned one specific technique, like one specific experimental technique to determine experimentally the enthalpy of a reaction. And this general idea is calorimetry. It's called calorimetry. It's called calorimetry because something calories and you're measuring them. I don't know. Don't ask me. First thing, like I'm not here to teach you chemistry. I'm here to teach you physics and then claim it's chemistry. That's what I've been doing for the last 2 hours. Anyways, so enthalpy. We said enthalpy is the change in energy. Well, we're going to make the following assumption, and I'm going to claim, and you're going to believe me. Once again, without any justification or proof. Enthalpy, like the energy change, is often released as heat. As heat, right? Well, like when you have a reaction that happens, the environment either like heats up or cools down. Something happens with it, with heating up and cooling down. Do people agree with that? Changes in energy often associated with like heat. And how do we know that there's like a difference in heat? We can observe a change in temperature. Do you agree? So if we assume the enthalpy of a reaction is the like heat released or absorbed by the action, we can observe that by looking at the changes in temperature. So now our question goes from how do we experimentally determine the enthalpy of a reaction is how do we make a setup where we can conveniently measure the change in temperature of whatever the reaction is doing. And then how do we convert this change in temperature enthalpy? Does that make sense as a question? Like the reasoning for this. First, we wanted to say, how do we find the enthalpy of reaction? We are going to assume that enthalpy is the same thing as just releasing or taking in heat. And now, heat we can measure through temperature. So now we can just need to design an experiment where we measure the temperature change of the reaction. And then we need to find the math to convert from temperature to energy. This idea makes sense of what we're now, how we're trying to approach this question. Yes? I need like everyone to nod. Okay, good. I'm going to briefly like do an aside, and we're going to introduce the terms endothermic, exothermic, because those are relevant. Those are probably the more relevant terms out of the terms you learn in this unit. Actually, the word enthalpy is useful. The words endothermic, exothermic is useful. And then maybe the word entropy and Gibbs free energy are going to be useful. But that's it. Like there's 6. So a few words that you need to know. The rest are just like basic English, like the who, what, where, when, why questions, gas, liquid, solid, lots of words. I love biology. That's you're not welcome here anymore. Actually, no, biology is fine. Biology is kind of hype. I've seen some stuff that they do. It's kind of interesting, but only kind of interesting. Endothermic and exothermic. Endothermic means that the system, and in this case the reactants and products, takes in energy. Takes in energy. Right? They absorb energy. Exothermic is system releases energy. Energy. So if the system takes in energy, so let's say you're going from state A to state B, right? Suppose this is endothermic. Endothermic. So the system took in energy. So what is the change in energy? Is it positive or negative? If the system took in energy, then the thing is positive or negative? Change in energy is
Positive.
Positive, positive. Because you take in energy, so you added energy, so you're in plus. Now, A to B, if you're exothermic, then delta H is positive or negative? Someone has to say.
Negative.
Negative, okay. Yeah, see, Iris, that answer is better than doing whatever that is. Okay. Okay. System releases energy, system takes in energy. Now, what does this is we're talking about the reaction itself, like the products and reactants. But these products and reactants, they aren't in like vacuum in nowhere. They have something around them, like beakers and other things in reality, right? And we're going to call that the environment. So let's look at what happens to the environment during an endothermic reaction. In the environment. If the reaction takes in energy, right? Does the outside environment get hotter, colder? So you have your reaction happening here, and this beaker is the environment. If this reaction thing gained energy, did the environment gain or lose energy? If this gains, does the environment gain or lose?
Lose.
Lose, yes, because this has to like take in energy from somewhere. So the environment lost energy, so it got colder. And then in the exothermic reaction, if your reaction releases energy into the environment, then the environment gets hotter. Okay? So we've now deduced that, hey, we have this thing where the environment gets hotter or colder. And maybe we can measure the temperature of the environment instead of the reaction, but we'll get to that thought later. Okay. So what did I say here? I said that we want enthalpies released at heat, and we want to observe a change in heat, so a change in enthalpy, as a change in temperature. So now we have the following theoretical question. So we can measure temperature, but how do we relate? So we can measure temperature because we have thermometers. Don't ask me how they work. They're magic. All of them. Even the mercury ones. The mercury ones make sense, but the other magic. We can measure temperature. How do we convert temperature? Convert temperature. Temperature to energy. To energy changes. So how do we convert changes in temperature to energy changes? Well, there's a couple things you need to know about temperature. One thing I'm going to say is going to be like a thing we're going to use later, but it's going to help you understand a little bit better what there is. And then the other thing, and then we're going to get to the actual content relative to this directly. Okay. Okay. Did I put a 1 in here? This is a 1. So we have the following. How do we convert temperature to energy changes? Well, first of all, we should figure out what temperature even is. Because temperature, we talk about it very often, but what does it mean? What is temperature? This is like a fundamental question. What is temperature? Well, temperature, we say, like, intuitively you think, okay, well, we measure how hot or cold something is. Okay, so then the following question is, what is hot and cold? Okay, well, my best answer for that is, if we know everything is made of atoms, and atoms jiggle around, this jiggling is the hot and cold. The faster the atoms jiggle, the hotter the thing feels. The slower they jiggle, the colder the thing feels. So we can say, hey, temperature is a measure of hot and cold. So it's a measure of how fast the atoms are jiggling. Does that make sense? How I got to that conclusion? Okay. Jocelyn, you look confused and scared. Are you okay? Okay. Right. So temperature, we will define temperature as the following. So definition. This is our second definition of the day. Temperature of an object is the measure of the average kinetic energy of particles in an object. In that object. Now, this is a poor definition because it refers to kinetic energy, and we've never talked about kinetic energy. So let's define kinetic energy. Kinetic energy is given to us by the following formula. 1/2 mv squared. M is mass of object. V is speed of object. Now, we all remember that, hey, we defined energy as energy differences. We don't know what the energy of an object on its own is, so this must represent some kind of difference between two states, right? Because we've always talked about energy only as differences. And it is. This formula actually gives you the work you need to put in just physically pushing an object of mass m from rest to get it to move to speed v. So if you had like a particle and then you started pushing it, you would need to put in this much work to make it go from rest to speed v. Does this make sense? Okay. And this is why we have an absolute zero. We have an absolute zero of kinetic energy when all the particles are at rest. But then if you're a physics person, you say, well, in what reference frame are they at rest? And then it all gets confusing, and then, things happen. But for chemistry, we don't care about reference frames. It's too difficult for a chemist to think about, so we just don't think about it. We have separate courses for that. Here we're interested in particles. Okay, so we have kinetic energy. So temperature is then, you take every single particle in your object, you measure its mass, you measure how fast it's going, compute the kinetic energy of that single particle, add all of that up together, all of the particles, and then divide it by the number of particles you have in total. As you can guess, that's probably not how most thermometers work. And don't ask me how they work, because that's how I think they work. Anyways, in my mind, there's like a just... Okay. I'm not crazy for the people watching this in review. Actually, no, I am crazy. It's just that I'm not that crazy. Okay, from physics, yes. So I did say that there does exist an absolute zero, but this is still not an absolute energy. This is still like an energy of going from rest to going to the speed. We only can talk about energy differences between two different states rather than anything else. Anyways, so this definition of temperature, what were we initially asking? How do we relate a change in temperature to a change in energy. Well, this is really not helpful. The fact that we have to like sum over all of the individual particles, we can't do that. That's crazy. Which is why we're going to look at stuff on the macro scale. And on the like macro scale, looking at like big chunks of things where you have a lot of particles, turns out you have a very easy formula to relate temperature to the thing. Delta Q, the change in energy, is equal to M times C times temperature initial minus temperature final, where M is the mass of the object. M is the mass of the object. C is the, I think it's called specific heat capacity constant. And I think, Lindsay, you did physics, right? You remember this from physics. You should remember it from physics.
Wait, sorry. It's Ti and Tf, right?
Ti minus Tf, yes. You can call them whatever T's you want. It's just that the first one is initial temperature, and then Tf is the final temperature. And you're going to understand why I use this specific convention in a second. Because you'd think it should be Tf minus Ti, because if something heats up, actually, you know what? Let's go with Tf minus Ti first, and then we're going to talk about it later. Tf minus Ti. Okay. Tf minus. So, what does this mean? The specific heat capacity, like the whole difficult part of this equation is understanding what the specific heat capacity constant is. Well, this is kind of a very engineering-esque trick. Just plug in an arbitrary constant that you get from experiment and just use it and say it works. Because this doesn't actually tell us much about how heat or temperature works, this equation, but it lets us do computations. So from an engineering perspective, it's quite good. So what does the C constant mean? The C constant, imagine you have this material. You have like some block of wood, or I don't know, block of metal, whatever it is. It has a mass M. And then you heat it up and it went from like one temperature to the other temperature, right? And you want to find out how much energy was put into that block to change the temperature from that temperature to the other one. Well, it turns out from experiment, people noticed that to heat up a certain object, the mass of the object by 1 degree is always the same. So the energy you need to put in to heat up 1 kilogram of something by 1 degree is the same, going from 26 to 27 degrees, is the same amount of energy as from 30 to 31 degrees, as it turns out. So C is the number in joules of energy that you need to put into the object to heat up 1 kilogram of that object by 1 degree Celsius or Kelvin. Does that question make sense? Does that statement make sense? Yes or no? C is the energy you need to put 1 kilogram of an object to heat it up by 1 degree. Yes, no, does that make sense? Hi, Sylvia. Can someone nod or not nod or disagree? Okay, that's good. Okay. And for each material, this, sorry, someone said something in chat. Okay. For this material, for every material, this constant is different. So the amount of energy you need to put into wood to heat it up by 1 degree is different from the amount of energy you need to put into metal or water to heat it up by 1 degree. Do you agree? Okay. Okay, now we found a formula. We know a formula to convert from temperature, changes in temperature to changes in heat. So yeah, from changes in temperature to changes in energy, right? So now the idea is the following. we want to take our reaction, measure the change of temperature in our reaction with a thermometer, and then use this equation for it. Does that make sense? The issue is, what is our reaction? Our reaction is some reactants and products. And you would think that, hey, then I have to like measure separately the temperature of the reactants and the products, and I'm going to need to know the C constant of both the reactants and products. But that's very difficult to do. Like if you have something, if you have like some gases like doing something to each other, like finding the C capacity of like multiple different gases and then keeping track of the temperature changes of all of the gases, that's very complicated. That's not easy to do. Do you agree? So we can't just directly use this. We need something else. We can't directly measure the temperature change of the reaction. We need something else. And this is where me talking about the environment comes in. This is why the environment is so important. Where did I talk about the environment? Here, endothermic and exothermic. Where's this? I'm gonna like separate this, call this number 3, and we're gonna move on. Right, so we can't directly measure temperature of reaction, because that's just too difficult. So need something else. Well, remember what I said before. Suppose you have some beaker, and then you have the reaction going on here. This is the reaction. And this is the beaker, right? If the reaction uses up some energy or releases some energy, we said that the environment is also going to change temperature. Do you agree? So we said if reaction absorbs energy, releases energy, beaker will absorb it. So beaker, the environment, so let's call it the environment. Environment, or the beaker, will absorb it. Do you agree? Does this make sense, this idea? Yes, no, someone? Okay. And so now, hey, we can, like, suppose we assume that all of the enthalpy gets absorbed, like all of the change in energy, all of the energy released by the reaction is heat, and all of it goes into the beaker. The beaker absorbs all of it. So suppose we make that assumption. Well, now we can very easily measure the changes in temperature of the beaker, because it's a beaker. That's pretty easy to measure the change in temperature of. And it's quite easy to know the like specific heat capacity constant for a beaker, because regardless of what reaction you do in the beaker, the specific heat capacity of the beaker is always the same. So instead of observing the reaction itself, we're going to observe what the environment does, right? And now if the environment got hotter, that means that the reaction released energy and got colder, right? So we just need to flip the signs of the energy, right? If we deduce that the beaker gained energy, that means that the reaction released energy. So if beaker is positive, then reaction enthalpy is negative. Do you agree with that? Yes, no? So now we observe, so I said we observe reaction from environment. And now let's look at our equation. Now we said, hey, delta Q, the change in energy of the reaction, is now going to be the mass of the beaker, so mass of the environment, or like whatever environment is directly around it, mass of environment times the heat specific, the specific heat capacity of the environment. And now we're going to do Ti minus Tf. Why? Because we said that the change in energy of the wait, you know what? I'm gonna do it the following way. Sorry. I'm gonna do it the following way. We said that the change in energy of the reaction is negative of the change in energy of the environment. Sorry, right? I'm backtracking a bit. Forget what I said before. Does this make sense? The change in energy of the reaction is negative of the change in energy of the environment. Yes? Do people agree? Now, the change of energy of the environment we can compute by looking at the mass of the environment, so negative of the mass of the environment, times the heat specific capacity of the environment, specific heat capacity of the environment, times the final temperature minus the initial temperature of the environment. Okay? But now we can factor in this negative into here and get that the change in energy of the reaction is the mass of the environment around the thing, the specific heat capacity of the environment times the T initial minus the T final, right? So now we get this formula. So we found a way to find the heat, the enthalpy of a reaction based on observing the environment. See, all of these variables are environment, the stuff around the reaction, not the reaction itself. And this is very convenient because it's much easier to observe a beaker than like some particles doing some stuff. Okay, I'm going to stop here for a second. Any questions? Does this make sense, what I just did?
Wait. Sorry.
Mm-hmm.
Why is it TF minus TI for the first equation again?
Okay, yes. So we said the following. We said that if an object changes temperature, right, then the energy is TF final temperature minus initial temperature. So think of it this way. If your thing heats up, right, then TF minus TI is positive, right?
Yeah.
Positive.
So I understand now. I wrote TI minus TF in my notes, so I got confused.
Yeah. I rewrote it the next time. So
Okay.
I'll still explain it one more time, just because it went up. So if an object heats up, this is positive. So overall, your change in temperature is positive, right? But but it's very difficult to observe the change in temperature of the reaction. So we make the following assumption that whatever the energy of the reaction is, the change in energy of the environment is the exact opposite. So we say Q reaction is negative of the Q of environment. And now we just write this formula for the change in energy of the environment, where you have the mass of the environment, C of the environment. But we now have this negative in front of it, and we can factor in the negative into T initial, T final, and get Ti minus Tf is the change in energy of the reaction. Okay, hopefully this makes sense. Now, using this fact, we're going to construct our apparatus, our experimental setup. It's called, and we're going to call it a calorimeter because that's what people call it. Calorimeter. Okay, any questions? Lindsay looks like stressed. Okay. Calorimeter. What we're going to do is the following. We're going to have a coffee cup. Coffee cup. Coffee cup. One of those like styrofoam ones so that they don't conduct. Yeah, we're not saving the turtles today. I'm sorry. Coffee cup. We're going to fill this coffee cup with water. This is going to be water. We're going to have like a styrofoam lid. And through that lid, we're going to stick like a thermometer into the water. And this is going to be our thermometer. And it has like a little window, and it has its silly little insane reading, which never correct, like 3,000 degrees, because it's the school thermometer and it's broken. Okay. Or maybe you're just bad and don't know how to use it. It's always one of the two. But I like to say it's broken to claim that I'm not dumb. Okay. And then we're going to have a reaction inside of the water. And sometimes you can like just have your reaction as like aqueous and just throw the chemicals in and let them do their thing. Other times you have something like a bomb calorimeter. Where, for example, you want to find the enthalpy of combustion. You want to see something. So you take like a metal cubic box or something, right? And then put it inside of the water and have whatever is combust inside of the metal box, but the metal box will heat up the water. So the idea is we have the reaction happen inside of the water. We assume that all of the energy it releases or absorbs is dissipated into the water. So we measure the temperature of the water as the temperature of the environment. And we always know the mass, and we can always easily compute the mass of the water, and we can easily compute the, we already know the C constant of the water from thousands of years of experiments. And this way, using our equation that we've derived above, we can find the change in energy of the water. And if we find the change in energy of the water, we can just take negative of that and say, hey, that's the change of energy of our reaction. Does this experimental setup make sense as to what we're doing and why we're doing it? Give it a moment to think. Or you have questions? Someone? Wait, my thing did something weird. I'm confused. No? Okay. This makes sense, yes? Nods something. Yes, okay, no one's saying anything, so I'm gonna pretend it all makes sense. Okay. Now, to be able to simply measure the temperature of water and plug stuff into this formula, we are kind of making a lot of assumptions here. We're making the following assumptions. How do you spell assumptions? Is it 1S or 2S? 2S's, 2S's, assumptions. We have the following assumptions. Eileen, stop laughing. Do you have a question? Okay, no, you just wanted to laugh on camera, okay. It's mostly what you've been doing for the last couple hours. The first assumption we're making is all energy difference, all enthalpy is some change in heat. All enthalpy is some change in heat is like released, absorbed as heat, is change in heat. And all heat from reaction is absorbed by the water. Is absorbed by the water. By the water. This is like when we make this calculation, this is an assumption we're making. Because we're not measuring the temperature of the reaction, we're measuring the temperature of the water. So we assume, by doing that, we're essentially assuming, hey, all of the enthalpy from the reaction goes into the water as heat. Does that assumption make sense? In this setup, okay. The next assumption is there is no exchange in heat, between the water and the cup and coffee cup. And then the last assumption we make, or actually maybe there's like another one. Actually, no, there is another one. We also say there's no exchange in heat between the cup and like outside environment of like the stuff outside the cup. Okay, we also make this assumption, or at least like we're not assuming that, like we're assuming all of these things are negligible to our calculations. And we also assume that if we are dissolving our reactants in water, then the concentration of reactants is very low. Of reactants in water is very low. In water is very low. Why does this matter? Because once again, we're using the C constant. We're using the C constant for the water here. So, and then, sorry, I'm going to write this. Q, the change in energy of the reaction is equal to the mass of the water times the constant of the water times T initial water minus T final water. Right? This converts from the change in energy of the water of the water this converts from the change in temperature of the water to the change in energy. And if the concentration of reactants was not like very small compared to the amount of water we have, then this C constant wouldn't exactly be just of water. This would need to be like the C constant of water and also the other chemicals around it if there were a lot of them. Does it make sense what I'm saying? Vaguely? Or ask a question? Yeah, so in this calculation, we're looking at the change in temperature of the water and looking at this C constant, which is how much energy do I need to put in to 1 kilogram of water to heat it up by 1 degree, right? So this formula inherently only works when you're looking at just heating up water, right? In our case, we have like some other reactants that we added into the water. And we better hope that these reactants don't absorb too much heat themselves, or like they have either the same specific heat capacity of water, or like this constant, or there's so little of these reactants such that we can just assume that they're not even there and just only look at the change in temperature of the water. So that this calculation works out, because we're using the specific heat capacity of the water and not of the water plus the reactants. That's the whole point. That's why we hope there's as little of them as possible. Hopefully does that explain it? Okay, good. And then I think there's like one more assumption maybe, but I don't remember it, so who cares? It is at this point that I would introduce to you the like concepts called like open system, closed system, isolated system, because this is where they become relevant. So I think open system is when you can exchange both mass and energy between your setup and the outside environment. Closed system is when you can't exchange mass, but you can exchange energy. So you have like a closed beaker, but you can heat it up and cool it down. And an isolated system is when you just have like, you can't exchange matter and you cannot exchange energy either. So here we're kind of assuming this entire thing is an isolated system. Like the cup with all the water and the reaction in it is an isolated system. No energy or matter enters or leaves. So okay, so I didn't prep a sample question for it. Let's do a sample question. I think first of all I should search up the specific heat capacity of water. It's in your data booklet, I think, or maybe it's not even. Like it's something you should memorize either way. It's important. Specific heat capacity of what? Is it like 4.2 something? Oh yeah, 4.2 joules per kilogram. So it's specific C of water. C of water is equal to 4,200 approximately joules per kilogram per degree Celsius or degree Kelvin. One thing to notice about this formula, why it's so cool, is that you don't actually need to convert from Celsius to Kelvin in this formula. Why? Because you're looking at the change in temperature. You care about what the temperature is at the moment, you only care about the change. And Celsius and Kelvin, you like move up in the same amount of steps. So yeah, that's irrelevant. But then once again, for all of your P or T, there it matters, because of course, Lindsay, you would know how the formula is derived and you'd be able to explain to everybody else why it's relevant.
physics. So not just me, Iris, yeah.
Yeah, oh, Iris as well. Or you would read my handout on, I think, my GitHub, which also derives that formula. Because I don't know, I found it a pretty derivation when we did it in class. When was it? It's like, damn, it's like 3 years ago. Okay, I'm old. Okay, then this, okay. Let's do a simple example. And let's say we have our, you're also a physics kid. Okay, cool. Well, I'm still gonna pick on Lindsay. Because I've seen her in class. I haven't seen Casey in class of physics. Okay, so let's say we have this reaction, A plus B turns into AB, where B are some like chemicals, and A plus B and it turns it into AB. Okay, fair? And let's say this is all aqueous, because let's just say that. And suppose I react, let's just do 4 moles of this with 4 moles of that. Let's make it very simple. 4 moles of this with 4 moles of that. Do you agree? The question is, what is the specific heat capacity, the enthalpy of this reaction per mole of A? Actually, no, let's do 2 and let's make this complicated. Like this, per mole of B. Do you agree? Now, actually, does this work out? I have 4 moles. I have, I'm gonna need 8 moles of this for this reaction to work out perfectly. In reality, you will have even more complicated questions where you might have a reaction that's not complete and things happen and okay. So we have this reaction, A aqueous plus 2B aqueous turns into AB2 aqueous. And we have 4 moles of this and 8 moles of this. 4 moles of A and 8 moles of B. Yes, question? No? No questions? Do people remember what moles are, vaguely? Okay, cool. All right, so we get our Starbucks coffee cup. Actually, are those styrofoam anymore? No, we want like the Starbucks from the 80s coffee cup. We put our lid, we put our like reaction, we stick our thermometer in 300 degrees. And suppose, and we observe, we make our reaction go. We have this water in here, right? And we observe the water change temperature from say 100, no, not 100, from let's say the 30 degrees to 40 degrees Celsius. Okay. Now, using this information that you're given, let's figure out what is the enthalpy per mole of B. What is the enthalpy of the reaction for every mole of B? First thing we have to do, we can find out how much energy was released into the water. We can compute that. And then once we figure out how much energy was released in total, we can figure out how much energy is released per single mole of B. So first question, how do we find the energy released into the water? What is the energy released into the water? How do we find it? Physics kids should know the answer. Take your time, think about it.
You plug everything into the Q equals MC2 and find Q.
Okay, well, delta Q, which change in energy is this? For what thing?
I guess we can, of the reaction.
Okay, sure, let's do reaction. Okay, sure, let's do reaction. Okay, let's do reaction. Let's actually convert this, that this is the change in energy of the reaction is negative of the change in energy of water. Let's do this so we kind of remember what's actually happening. Okay, change in energy of the water. And then Q equals mCT, that's right. So we plug this into MC, negative MC T final minus T initial. M of what, C of what, TF of what, TI of what? Iris,
Of
enjoy your
water.
breakfast. Sorry, what?
Of water.
Of,
No,
so M of water, the C of water, and I forgot to say, let's suppose there's 2 kilograms water. Suppose that's the case. TF of water and TI of water. Notice that I have the negative factored out because honestly, using just using this equation where you do like Ti minus Tf for the Q of the reaction and talking about the environment can get confusing sometimes. Like it's sometimes nice to just write, hey, change in energy of the reaction is negative of what the water changes, and then just write negative times the change in the energy of the water is just more clear. That way you don't get confused as to what's happening. Okay, so let's plug stuff in. So the change in energy of the reaction is equal to negative 2 kilograms times 4,200 joules per kilogram per degree Celsius. And what is our change in temperature? It is, someone say it, 40 minus, guys,
30.
please. 30, okay, thank you. Okay, and then we some number, negative 2 times 4,200 times 10, so that's 8, 4 times 10 to the 3 equals 8.4 times 10 to the 4 joules, which is equal to, we convert this to kilojoules to be spicy, divide by 1,000, right? 8.4 times 10 kilojoules. Kilojoules, J, I think. Does this make sense? Jocelyn giving weird looks. Like, I don't know if that's just
My face
you're
just
confused.
does that.
Okay,
It
okay,
kind of
yeah,
thinks-
okay.
That's my thinking face.
Thinking face. Okay, that's good. See, people normally think when something is unclear. That's my issue.
What happened to the negative?
The negative? Well, oh, you're right. Shut up. Yeah, there was a negative here. You're right. And this negative is consistent with our definition of exothermic. Because why? We saw that the environment heated up. That means that the reaction must have released energy into the environment. So the change in the energy of the environment of the reaction is negative because it lost energy and gave it to the environment. So it's a negative. Okay, I'm going to give people a moment to think on this. And then we're going to move on to the next step. I have to return a book to the library, but I think I'm just going to extend it.
Okay, I have a slightly
Yes.
unrelated question, but you know that like little box you drew earlier, is that relevant to this?
I drew many boxes actually, like
Oh, sorry,
3.
like the little cube thing you were talking about combustion, I think.
Yes. So the idea is right now we're talking about like we have our reaction where we just put A and B's just into the water and just they're aqueous and they're floating around and they're reacting in the water,
Okay.
right? But suppose you had like a combustion reaction, like you were burning oil and you wanted to see how much energy is just burning oil release, right? You can't burn stuff inside of water, or at least it would be quite difficult. So instead, you make like a box or something. You put the oil in the box with the oxygen. You somehow light it up, like you put the box in the water, light up the stuff inside of the box, have it combust inside of the box, and then hope that it gives off the energy of the combustion inside the box, gives off the heat to the box, which then gives off the heat to the water.
Why
So
don't you
the idea is you're not only limited to doing like aqueous reactions with this method.
So why don't you just measure the temperature of the box?
You could do that. You could do that as well.
Oh, okay.
But that metal loses heat very fast. I think like it's just it loses heat faster than water, and water needs like just water is better.
Okay.
Because
Yeah.
water needs a lot of heat to be heated up, and combustion reactions usually release a lot of heat, and you don't want to like burn things and things be dangerous.
Okay. Thank you.
I don't know. It's just like that's what they do for reasons. It's just more convenient. Stuff floating on water is, I guess, just nicer than a metal box. What if the metal box explodes if it's in water? I'm just making up things. I don't actually know. I don't actually know any of this.
It's just not okay. I had another question.
I came up with all of this yesterday. It's all false. It's all fake and not true.
It's right out of your head.
Yeah, like straight up, I'm making things up on the spot. Okay. Now we've completed the first step. We've figured out how much energy was released into the water. But what was the question? I asked you, what is the enthalpy per mole of B? Right? Per single unit of B, how much energy is released? Well, now we know how much energy was released total. How many moles did we use? We used 8 moles of B. So if for 8 moles of B, so the delta H for 8 moles of B is negative 8.4 times 10 to the something, 10 to the 10 to, yeah, just 10 kilojoules, right? Then the delta H for 1 mole of B is negative 8.4 divided by 8 times 10 kilojoules. Do people agree with that? That's a simple statement. Yes? Okay. Now, I'm going to give another second, okay? And this is because we combusted, not combusted, we aqueously reacted 8 moles of B. Now, if we know that for 1 mole of B, I produce this many kilojoules. Actually, this should be what? This should be 1.4. We divide 4 by 4, we get 1.05, like this, kilojoule times 10 kilojoules. Oh, but then you like significant figures and you got to round up. And because sig figs, you do 1.1 times 10 kilojoules, right? Because you got to round up. Sig figs are important. That's how you lose. See,
It's also
the
still
better.
negative.
Shut up. So it's a test. Okay. Right. Sig figs. There's the following rule. The less mistakes you make on your test, the more marks you lose for sig figs. So once you understand the chemistry of what's happening, your next step is to figure out sig figs, because you can lose as many marks on sig figs potentially as people lose on having wrong chemistry. And it's just the truth of life. So you have to learn to use sig figs. I still haven't learned how to use sig figs. I have only figured out uncertainties, and even then only when I have a computer. And like all of Intel's and what's it called? IBM's supercomputers to calculate uncertainty, because I just make the most inefficient ways to do it. Okay, now one last question. Well, not last question, the next question. The last question related to this scenario is, if I know that, if I know that for 1 mole of B, I have 1.1 times 10 kilojoules of energy, what is my enthalpy per 1 mole of A? Right? What is my enthalpy? Yes, you can just say stuff.
Okay, I don't want to interrupt. So your delta Q is just your delta H? It's working?
Yes.
Oh, okay.
Well, like my delta H in this specific case is the enthalpy per mole of B. Not just the energy you've released, but the energy you release after reacting 1 mole of B. My delta Q in this case is how much energy we've released after combusting 8 moles of B. Or not combusting, like reacting 8 moles of B. Do you agree? Yes?
Okay.
And that's why we divide it by 8, because we want to see, well, if I use up 1 unit of it, what's the energy I release? And that's why enthalpy is always written per mole of something. Because if you react more of something, you're going to release or absorb more energy. So it's not useful to just say like, oh, the enthalpy is this. Enthalpy per mole of what is the like key thing. You always have enthalpy per mole of something. Or you can say like, for this specific reaction, the change in energy is this. But,
I think I get it. I think I get it.
You think you get it, okay. And we figured out, so the delta H in here is equal to negative 1.1 times 10 kilojoules per a single mole of B. Yes? And are you confused by the banana or the chemistry? Okay, both. Okay. Okay, now if we wanted to write out our enthalpy per mole of A, right? This is per mole of, whoops, I'm going to separate this. Okay. This is our enthalpy per a single mole of B. So for every 1 thing of B that we react with this reaction, we release 1.1 times 10 kilojoules of energy. Now, suppose instead of asking for if we react 1 mole of B, what if we react 1 mole of A? How much energy do we produce in this case? And it's still the same reaction. Remember, for 1 mole of B, how many moles of A do I have? Like to react 1 mole of B, how many moles of A do I need to have a complete reaction?
Half a mole?
Pardon?
Half a mole of A?
Half a mole, correct. Because if for 1A I need 2B, then we divide that by 2 and get that for 1B I need half an A, right? So if I react 1 mole of B, right? That means I've reacted half a mole of A. Do you agree? And if I want to react 1 mole of A, I need to multiply this. We can write this as the following, times 10 kilojoules. 1 mole of B is the same thing as reacting half a mole of A, right? That's what we get from our equation. And then this half ends up, it's at the bottom, so you multiply by 2. So it's negative 1.1 times 10 times 2 kilojoules of moles of A. Do you agree? And you get negative 2.2 times 10 kilojoules per mole of A. And these are both, this negative 2.2 times 10 kilojoules per mole of A and negative 1.1 times 10 kilojoules per mole of B are both equally fairly enthalpies of this same reaction, because you can always convert between the two of them, right? Both of these represent the energy released for this reaction. Does this make sense? Spend some time to think about it? Okay, yes. Now, the other thing, and then the enthalpy a single mole of AB2 produced is going to be the same as the enthalpy of A, because for a 1A, I produce a 1AB2. Yes? For 1 mole of A, I produce 1 mole of AB2. So the energy released in using up 1A is the same thing as the energy of making 1AB2. Okay, if anyone has questions about that, you have a chance to ask it now, or forever remain silent. Okay. Okay. So we've done this. Okay, and now we found a way to compute our enthalpy per mole of whatever. Given, like, if we can make the experiment, right? Yes? We've successfully answered the question that we originally asked. We asked, hey, how do we experimentally find enthalpy of reaction? Well, I've suggested to you some vague procedure, and then we have some formulas, and then we measure the temperature of the water, and then we get our enthalpy, and then we get stuff. Now let's see if we can make this procedure any better. And let's see what's wrong with it to begin with.
Wait, the last
Yep.
enthalpy that we found, that's the enthalpy of A, right?
The enthalpy, it is the energy released when you react 1 mole of A. So energy per mole means what is the change in energy if I do this reaction with 1 mole of B or 1 mole of A. And for every 1 mole of A, I have double the B.
Wait, for 1 mole of A, if you want to find the like change in energy, could you also just take what's it called, delta Q and divide it by 4, or?
Yes, that's the same idea. It's just that like you could, instead of delta Q, instead of dividing it by 8, you divide it by 4. That's correct. However, sometimes like they ask you, you can have a question like, you're given the enthalpy per mole, you're just given the reaction, you're told, hey, here's the enthalpy per mole of B, what is the enthalpy per mole of A? Like that's a question you could have. So you should be comfortable with converting them either with the Q or just directly. If you're given the enthalpy per mole of B, you should be comfortable with converting to the enthalpy per mole of B. But yes, that's correct.
All right, thank you.
That's the right thinking. And if you notice, it's the same thing. Dividing by 4 is the same thing as dividing by 8 and then multiplying by 2. And dividing by 8 gives us the enthalpy per mole of B, and then to convert, we multiplied by 2. And okay, we got the same thing. Okay, but actually here, like I got more uncertainty for whatever, because I sig figs, so it doesn't matter. Okay, we've done this. Now, this,
Sorry,
oh,
quick
yeah.
question. So that means the like enthalpy from A and B, like the reactants, aren't the same as the enthalpy of the products? Wait.
So when we say the enthalpy per mole of something, we say the energy released after you've reacted this many moles of that something. So in this specific reaction, I use 1 mole of A to produce 1 mole of AB2. So the enthalpy per mole of A is the same as the enthalpy of producing 1 mole of AB2. Does that make sense? Because enthalpy per mole of A says how much energy is released by this reaction in total if I've reacted 1 mole of A, right? And if I've reacted 1 mole of A, that's the same thing as saying I produced 1 mole of AB2. So that energy has to be the same. However, if I react to 1 mole of B, that means I only reacted half a mole of A. Does that make sense?
Yeah, so you don't really do any, like, the enthalpy of A and B are like, well, they're related because you're reacting both of them at the same time, so it's like a related
Yes.
quantity, but you don't, but and there's no, like,
The enthalpy is associated to the reaction in general. It's just that we choose to look at it from the perspective of us using up A or us using up AB2.
okay. Yeah, I see. So you
It's
don't
like it's associated to the entire reaction. It's not like you're looking at an isolated thing. It's just that you're saying like how much of the reaction we're doing by specifying how much of A or B or AB2 I'm using. Because if you know how much A you used and reacted, how much A you reacted, then you know exactly how much AB2 you produced and how much 2B you used up as well, right? It's just a way of us saying, hey, how much stuff are we reacting? And you're just looking at perspective of, are we reacting A or are we producing AB2 or are we reacting B?
okay, I see. Thanks.
It's all the same thing, it's just a different way of counting the same thing.
Okay, thank you.
Right, because in the end, if you were asked, oh, how much energy was released if you reacted this many moles with this many moles of this and that, you would always get the same answer, regardless if you use enthalpy per mole of A or enthalpy per mole of B. Okay, good questions, because like these, you're asking all good questions because there's things that do trip people up, and it's good that you're asking them now. and not when you actually do chemistry. Because like my physics professor in first year said, the easiest way to learn something is to learn something you already know, or it was something along those lines. It's very easy to learn something that you already know. So that's what we're doing. That's what we're trying to achieve. Okay, and we're soon going to be done, maybe one day. What is the problem with this process? We want to, let's try and find a way to improve on this process. And what are the problems with this process? The problems with this process are all of these assumptions, because we assume all of these things and all of them are false. All of these assumptions that we make are all false. None of this is true. I'm lying to you. Because heat, like enthalpy, all of it changes in heat. No, maybe some of it just like changes pressure or something in whatever, and that doesn't affect it. Or all the heat of the reaction is absorbed by the water. Why? Why would that happen? What if the water absorbs some of the heat and then the reaction like is just faster? Like the molecules of the reaction just start moving faster. No heat exchange between the water and the coffee cup. Your coffee cup gets hotter when you put hot coffee in it. So that's false. Okay? No heat exchange between the cup and the outside environment. When you touch the hot coffee cup with coffee in it, you feel how it's burning your hand. So that's also false. All of this is false. None of these assumptions are true. So, and okay, they're good enough in some scenarios, but can we possibly improve on this? Well, okay. Consider the following scenario. Instead of taking a measurement before the reaction and after the reaction, we're going to keep taking temperature measurements while the reaction is going. Taking temperature measurements inside our cup. Temperature measurements inside cup. Inside cup. Over the time of reaction going. Of reaction happening. And suppose this is an exothermic reaction, so the temperature of the water increases. So let's say this is the initial temperature of the water, and okay, we have a few seconds where the temperature is like initial. Then the reaction starts happening, and it starts releasing some energy. Okay? And then the reaction stops at around this point, and then the coffee cup, the water starts like losing energy to the environment. Do you agree? So this is reaction starts. Reaction starts. This bit, sorry, I should label the axes. This is time as time progresses. This is T temperature. So yeah, temperature. In, let's say, degrees Kelvin. And this is degrees Kelvin as time in seconds. Doesn't matter. So reaction starts, reaction stops. Do you agree? And this is what we observed from our cup. Does this graph make sense why it looks kind of like this?
Wait, sorry, are we talking about like an improvement or like a problem?
I'm saying the same. We're going to do the experiment in the exact same way we did before. Like the experiment itself, identical. We do the exact same things. We have the same coffee cup, we have the same lid and thermometer. That makes sense, yes? Mm-hmm. But before I said we have an initial measurement of the water and then after the reaction happened. I'm saying now, instead of just collecting those 2 points of temperature information, let's measure the temperature every like 1 second.
Okay.
Okay, and we're going to use this additional information to fix most of these issues given by these assumptions. We're going to take more measurements and we're going to correct using our data. We're going to do like a correction. And actually, I want to move this graph because this graph is going to get tall. And this is like a difficult explanation because like it's intuitive once you get it, but it's confusing. It's confusing to explain. In other words, I don't know how to explain this in a good way, so you're gonna have to like really focus. Okay, I'm gonna make this taller. It's a surprise. This axis taller, and because that's a surprise tool that will help us later. Okay, let's analyze this graph. And this is temperature of water. This is the temperature of the water. Let's analyze this graph, and maybe don't copy all of this. Copy the graph down, listen to what I say first, and then I'm going to give you a couple of minutes to write whatever you want. Just really focus on this. Let's look at this graph and see what is actually happening. So here, there's nothing happening in the water. We're just measuring the base temperature of the water to know our initial temperature. All right, makes sense? Yes? No? Good? Okay. Then our reaction starts happening. We turned on our reaction, and it starts releasing energy into the water. And then the temperature of the water peaks here. So you would think this is the highest temperature of the water, right? That this is like final temperature of the water, right? That's what you'd think initially. Okay, and you would say, okay, I have my T initial, I have my T final. Let's plug it into the formula and do the exact same thing. That's what we just did before. We took this T initial, we took this T fake final, yeah, T final, and we plugged it into our formula and did a calculation. However, that was under the assumption that we don't have any losses of heat and energy to the outside stuff outside of the cup or the cup itself. However, if we look at this graph after the reaction stopped, we can clearly see that it's cooling back down and definitely losing temperature. So it cools back down to like its original temperature of the environment and stays at the same temperature. So we clearly see our assumptions are false, right? However, you can notice that per second, this is a line, right? This is a line, a straight line. That means that per second, you lose the same amount of temperature each time. Each second, you lose the same amount of temperature, right? So look, if we were losing energy the same amount per second, when the reaction stopped, then probably we were also losing temperature per second during the time that the reaction was going on, right? So when the reaction was going on, we were probably also losing energy. Do you agree with that? Yes? Okay. And the other thing that we can kind of guess is, hey, we have a very specific slope. We have a rate, K. We have a slope for this line. We can, from this graph, we can compute exactly how much energy, how much temperature we lose every second of us being, like of the cup just sitting there, right? Yes? Do you agree with that? So we can, it's quite safe to kind of guess that we were losing, like when the reaction was going on, we were losing temperature at the exact same rate as we were after the reaction stopped. Does that make sense? So if say I was losing 1 degree every second, my temperature was decreasing by 1 degree until we got to like the temperature of the room, then I would imagine that I was also losing 1 degree of temperature every second while the reaction was going on, right? So like it was heating it up and cooling at the same time. Do you agree? So if we look at this delta T of how long the reaction was going on for. So delta T is how long reacted for. If we multiply this delta T by this slope times K, this would give us how much temperature was lost while the reaction was going on. That makes sense? Because if we're losing K per second and the reaction went delta t long, then K times delta t is how much we lost during the reaction. Yes? I need like everyone to nod. Like this is important. Okay, everyone's good. So in that case, we can say, hey, our highest final temperature is actually this T fake false plus delta T times K. Do you agree? So therefore, sorry, not plus, K is negative. So therefore, T final actual is the T fake final minus, we subtract off the stuff that we lost. Like K is a negative slope, so this is like negative. So minusing it is going to plus it. Does that make sense? Right, we're just adding back the temperature that we lost while the reaction was going on to this bit. We're just adding up all of the energy that we lost in this time to our final temperature here. Do you agree? Eileen looks focused. Iris is nodding, Casey is something. Okay. Yes, everyone is okay now. This makes sense. Okay, good. Casey, you nodding harder doesn't make everybody else nod harder. It's like if I'm asking, it's not because I'm asking you, it's because I'm asking everybody else. Okay, so now we have a way to like, we've now found a way to correct for, let's look at these assumptions. We've now corrected for this assumption, we've corrected for this assumption, and okay, yeah, we've corrected for these two assumptions. We've corrected for the fact that heat does exchange with the outside environment. And now, see, here we assume that this is an isolated system, right? But here, we've now assumed that it's a closed system. And we've just corrected for the fact that it's a closed system. So this is a closed system. And in here, we were assuming it's an isolated system. Okay, okay, and I have one last thing before you can guys try and write stuff down. So this is a great formula. However, on a test, you're given this graph. And buddy, you're not going to be like counting squares to count the slope. You're going to be panicking. And that's why we have a graphical technique for how to do this. If we extend this line further, if we extend this line, aha, here. This is in fact going to be what? Look at this. This is T fake final, right? This is T fake final, right? Fake, exactly. But then this, if you look very carefully, this is a triangle. And this is delta T. This is delta T as well. And this point is delta T times K minus T fake final. Do you agree that this intersection of this line of where the reaction started with the extension of this line, this point is the same as T actual final? Because for this line, we travel delta T time at slope K, right? And we're just traveling backwards. This added bit is delta T times K. And this bit was already T fake final. So we just add them together to get this. Think about this first. Why is this well, this is like negative delta T times K. If we extend this line with the slope K, right? What does the K mean? K means for every second that passes, you lose K degrees, right? So going back along this graph is like you backtracking as if you were losing degrees from this like T actual final, and then you were losing degrees all this time from here and then got to here. Yeah, so in that case, you don't need to actually calculate the slope. You can just extend this line, then extend this line of when the reaction actually started, right? Find this point and then read off of the graph that says T actual final. Okay, does this technique for correction make sense? I'm going to give you guys a second to copy this graph down with whatever you like. I do not have I don't have a prepared image of this graph. This is all you get. You can copy it down. I'll send you these Autodesk sketchbook things. If you have questions, ask questions. I'm going to give you a moment about it. Let me move this. Okay. When you're good, just tell me. Like, say something in chat, and then we're close to done. We're just gonna speed run through a bunch of things that are like somewhat irrelevant. Well, they're relevant later, but they're like weird.
Wait, I think I missed a big chunk of it.
Yeah.
Talk to my brother, but what did you explain after the backpedaling part of it?
The backpedaling part of it. Well, no. Back with the graph, or like this backpedaling part, or this backpedaling part.
The graph back. I missed a lot, didn't I?
No. I just said that the graph backpedaling part is just this point. This point is the same as this point. Like, do you understand why this point of the intersection of these two lines gives us T final actual? Does that make sense?
Yes. Are we just copying?
Okay. Then I said, hey, if you don't get it, ask me like 10 times. Okay. That's all I said. You didn't miss much.
Okay. I'll copy.
And I also said, if you want to copy this graph down, you have a couple minutes. Tell me when you're good copying graphs. Then I'll send you these notes as well. But my handwriting is ugly, and like right now you understand what's happening. Later you'll forget. So best to like make your own notes.
I also have another question, which is when are we gonna finish?
I think we're gonna finish in like 20 minutes.
20 minutes.
Cool.
Okay. It is
Okay.
1:30 essentially.
I know. I'm sorry. I'm just trying to speedrun a month worth of content in
It's okay,
a couple
it's okay.
hours. And I mean, we're actually almost done through the entire unit. I added some like additional things. So far, things make sense, right? It's like triangles, circles, lines. Nothing difficult.
Triangles. Yes, I love triangles.
Yeah, exactly. Okay. Okay, now I'm gonna try and speedrun this a little bit because I'm also getting a little bit tired. I even turned on the AC today. No one told me it's gonna be like 28 degrees today outside. What is this? I didn't expect it to be like 29. I thought it's gonna be like 5, and I can just sit with my window open and have the wasps enter my room like usual. Actually, it's weird. The wasps, like I've seen wasps outside my window many times, but they've never figured out how to get in, even though my window's open. It's weird. Okay, are we good to continue? We're almost done. So, yes, no? Just like thumbs up. Are we good to continue? Okay, good. Now we just talked about enthalpy, right? Now we introduce a new kind of energy. We talk about Gibbs free energy. Gibbs free energy. And this is, so enthalpy, we said, the enthalpy of a reaction, we said, is the total energy that you need to like put into the reaction, like to go from like one configuration of atoms to the other one, right? The total energy difference. Gibbs free energy is going to be, it's called, defined as the non-expansive work done by the system. What does this mean? This means that if enthalpy is all the work you need to put into the system to make it go from one state to the other, Gibbs free energy is like all of the work minus the stuff with like particles moving, like spreading apart. So if you imagine like you heat up a gas, the particles start moving faster, but you also need energy to like have the gas expand, right? So Gibbs free energy is the enthalpy minus the energy you use, minus the energy used for the particles to expand. Does that make sense? It's all of the energy minus the part which is related to like how it physically fits in the world. I need a thumbs up because this is like an intuitive thing. It's a non-intuitive thing in the sense that in actual grade 12 IB chemistry, they never actually tell you what Gibbs free energy is. They just say, oh, there's this like number called Gibbs free energy, and like there's these like formulas with it. I think this kind of helps you understand these formulas. And we're about to introduce the concept of entropy. The change in Gibbs free energy is equal to the change in enthalpy minus T times delta S. So delta H we know, T is temperature we know, so this is Gibbs free energy. Free energy. And delta S is entropy. And as you can guess, it has units of joules per degree Celsius. Now, what is entropy? That's a difficult question. I still don't know exactly, but I can how to think about it in this context. We said that Gibbs free energy is the non-expansive work done by the system. So, in that case, delta H total work done on the system to get it from one state to another, right? Yes? That's the delta H is the total energy you put in to get from one place to another. So this must be the stuff that we subtract off that's responsible for like the particles spreading out or like maybe getting closer together. This is the energy responsible for the expansion of the particles in the thing. So entropy, I guess, is kind of the energy per degree. Actually, this is per degree Kelvin, per degree for particles like spreading out. Right? And notice that this always, T here is always in Kelvin. Always in Kelvin. And let's think about it. Does this make sense? Well, suppose T was 0. And if we have like absolute, the particles are all stationary. They're not moving at all. Right? Because remember, temperature is the measure of kinetic energy. If temperature is like absolute 0 in Kelvin, that means the particles aren't moving at all. They have 0 kinetic energy. So suppose we manage to like completely freeze all of our particles. They're not moving at all. Well, then this term is 0, and then our Gibbs free energy, our non-expansive work, is exactly our total work. And that does make sense, because if the particles are all stationary, they're not expanding. Right? So there is no expansive work. So then the Gibbs free energy is the total work. Okay. Kind of makes sense. Maybe. A little bit. Yes, no. Okay. So Gibbs free energy is the total energy minus the energy that you need like to expand to like for the particles to expand after the reaction's done. The change in entropy also obeys like a kind of Hess's law. So if you go from A to B, so if you go from A to C to B, the change in entropy here plus the change in entropy here is the same as the change in entropy from A to B. That's the thing. And you also, similarly, you have like entropy of formation, entropy of all these other things, like we saw at like a couple hours ago. Like we had these reactions and entropy was known for them. And let me see. Okay, I'll introduce spontaneity of a reaction, even though I kind of don't want to. So if delta G of a reaction is positive, no, is negative, let's start with negative, is negative, then I think, I'm not sure, I think the reaction is called spontaneous. Then reaction is spontaneous. Right? If delta G is positive, reaction is not spontaneous. Is not spontaneous. I'm going to give you guys a moment to write this down. We're going to chat about what it means. Then I'm going to tell you about the Maxwell-Boltzmann distribution. Actually, then I'm going to tell you a little bit more, and then we're going to be done soon, I promise. One day. Wait, I need to get the screenshot. Oh no, it unfroze. Damn it. Such a funny photo. Photo opportunity completely wasted. Okay. Are we done writing? Yes, we're good? Okay. Well, even if you're not done writing, that's your problem. Not mine. So why does this make sense? Okay, let's go back to our equation. Minus T delta S. Okay. If delta G is negative, right? That means one of two things. Either H is negative and S is positive, so the total energy, it overall releases energy, right? And it overall releases energy when spreading apart, right? And if our reaction only releases energy, well, it's easy to release energy, right? So the reaction is spontaneous. It just does it on its own. It just has enough energy to just release it. Like, does that make sense? Vaguely? Like, if it naturally releases energy, and when spreading up the particles also release energy, then of course the reaction is spontaneous. It likes to happen because all it does is release energy. That's on one thing. The other thing is, okay, what if delta H is positive, so the reaction gains energy, but then to spread apart, it releases all of it and it's still negative. Well, once again, then the particles want to fly apart and it's like spontaneous. Now, if the reaction takes in energy and doesn't spread apart enough, then like it takes in energy overall. Like it's difficult for it to just take in energy. And if the reaction both takes in energy and takes in enthalpy to like takes in energy and takes in enthalpy to wait, no, it's the other way. If the reaction wait, hold up. Wait, no, I messed this up. I messed this up. Forget everything I said. Forget everything I said. Wait, sorry. I'm gonna go and make the chart. I was trying to skip things. I'm gonna make the chart. Okay, delta H, delta S. Positive, positive, negative, negative. Wait, positive, negative, negative, positive, and then I think positive, positive. Negative, negative. Okay. Suppose the reaction. Well, let's start over. Forget everything I said. Don't think about it. Suppose our reaction is spontaneous. So overall, delta G is negative. Then we have a possibility where overall the reaction gains energy, but then delta S has to be, no, this is not possible. Sorry, this is not possible. This is not possible. This is negative, this is positive. This could be spontaneous. This positive and positive. This could be, no, yes, this is always spontaneous. This could be either. This is negative, positive, this could be either. And then this is non-spontaneous. Okay, let's start this over. If delta H is positive and delta S is negative, then overall this number is always positive, right? So delta G is always positive, right? Yes, does this make sense? Okay. And what does this mean? This means overall the reaction takes in energy, and then if delta S is negative, I think that the reaction like releases energy when spreading apart, and apparently it doesn't like that. I think that's how that's defined. I don't remember. If delta H is negative, it overall releases energy, and then it takes in some energy to like stay organized in specific organization. Then it still likes to do that because it still like releases energy, and then it doesn't release too much of it. I'm guessing that's the idea. So that's why that's called spontaneous. And then if they're both positive, then it could be either, depending on which one is bigger. And then if they're both negative, this is negative, this is positive. So depending on which one's larger, it could also be either spontaneous or non-spontaneous. But I think like the idea is something like what's more important to you, releasing a lot of energy and then wasting it on like spreading apart, and like one is favorable, the other one isn't. I'm honestly, I didn't prep this explanation last night because I didn't think I'd explain this. Okay. And now our last stretch of things. This is Gibbs free energy. We'll see it like maybe next week. Maybe we'll see it like Friday. Like sorry, Wednesday, maybe Friday. I don't know. Last thing are energy diagrams for reactions. Energy diagrams. Diagrams for reactions. Have you guys seen stuff that looks kind of like this? Yes, okay. So this is energy, this is time as the reaction progresses. A reaction. Yeah, we did this in bio. Oh my god. You probably
It
did.
could be like, what's it called again? Oxygen potential or something?
I don't know what it's called. I know this is how it looks like, and
Yeah.
I know vaguely what it says. The idea
I
is,
love bio.
yes, we all love bio. The idea is the following. As your reaction progresses, oh, Casey Gao wants to be added back. Okay, cool. As our reaction progresses, it is not like, it's not that the energy of the reaction, like the energy of the reaction there has to be some change in energy, right? So if we started at some state, some like energy level, some state, we're gonna end up at another one, right? But it doesn't mean that we directly just go like this, directly. Most of the time, for the reaction to get going, like momentarily, you need like more energy than you will have like be left over in the end. Like, oh, like it just drops down. And point is, this difference here is called EA, the activation energy for the reaction. And actually, normally this is like all talking about like the kinetic energies. So I think this is like all kinetic energies of particles. So in this case, it does make sense that we have like some E initial, because this is just like the energy of the particles above them being stationary. This is the activation energy, how much energy a particle needs to be able to start the reaction. That's EI plus, wait, is activate, yeah, plus E active, wait, is it, let me think about it. Wait, I forgot what EA is. Is EA EI plus EA, or is it like a fixed number? Hold up. Activation energy. I should have practiced. I don't remember how it's defined. What makes more sense? Okay, yeah. This is EI plus, yes, this is the activation energy. How much energy we need to add to our system for the reaction to go. Then this is the E final energy. And then if we do final minus initial energy, final minus energy initial, that should give us our enthalpy. But actually, wait, no, this is an exothermic. This represents an exothermic reaction, so it's the conventions are the other way around. It's confusing. EI minus EF, and this is equal to the enthalpy. Yes, I think this is like releasing heat. Wait, or is this the energy of the environment then? Let me think about this. Okay. Action progress. Sorry, exothermic reaction. Okay, yeah, no. This is not. I was right. I was right. Don't argue with me. It's EF minus EI. So we know that this reaction. So sorry, this bit is delta H. This is the change in energy overall, and the whole point, the whole takeaway of these diagrams, I think there's a lot more to be said about them. I just don't remember what. Is that for the reaction to stop happening, you need to like have particles that have above a certain activation energy. And not all particles have above activation energy. Meaning not all particles are able to react. Because if you have a particle whose energy is like, it doesn't have enough energy to get over this like lump, it's not going to actually react and then lose its energy away. The idea of this diagram is like the particle rolls along, it gets more energy than it's supposed to react, and then it loses some of that energy after it has reacted to get to our delta H. Does that make sense? Okay. The issue is not all particles will be able to gain this like extra activation energy and then give it off. Now, there's this following cool thing called the Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution. It holds for an ideal gas where all the particles are the same and of the same mass. And this distribution has the following equation. You don't need to know this equation. It's completely irrelevant to the course, but it is useful for developing some understanding of how certain things are interconnected, and we'll need it. We'll kind of reference it later. E to the negative mv squared over 2kBt. Okay, and this is going to look, this is, so f of v, this is a weird thing, and then this is v. I think this looks something like this. This is what this graph looks like. What does this graph tell us? Suppose we look at the area under this graph between points A to B. Look at this area S. S dash area under FV. We're almost done. Between A and B. This area tells us, S gives us the percentage of particles in the gas with speed above, with speed between A and B. So if you know this area, you can figure out what percentage of the particles have this kind of speed, right? Does this kind of make sense? If you draw this graph and your particles are of a given mass, Kb is some constant, T is a temperature, then this graph will tell you, by looking at the end of the curve, what percentage of particles have a speed between this number and this number. Now note, this graph is for a gas with particles of fixed mass at a fixed temperature. And remember, temperature is the average kinetic energy. So remember that average kinetic energy, like temperature, kinetic energy, temperature are kind of the same thing. You can convert between the two. So you could replot this graph, and it's just going to be a little bit scaled, as a graph of energy. So kinetic energy to whatever f of v. And now you can compute what percentage of particles has a certain amount of energy. So now S tells us percent of particles with energy between A and B. Okay? Yes, no, kind of, maybe. Does this like somewhat make sense what this graph tells us? The area under this graph is going to tell us how particles have an energy between A and B.
Why can't we change the V and the kinetic energy?
Good question. Because you can remember that kinetic energy is equal to 1/2 mv squared. Right? And in this case, like converting from V to EK, we get that kinetic energy is just like 1/2, like you can just like, hold up. If you look at this equation, see you have this V squared here. Yeah? If you can replace V everywhere, you can replace V everywhere with a square root of 2ek over m in this equation, and you're going to get a graph that doesn't look exactly the same, but it looks hella similar. Like instead of V squared, you're gonna have like some constant that, as you can recognize, this is some constant, is in kinetic energy, like by some other constant, times e to the power of negative kinetic energy divided by, okay, some other constant z. But like x times e to the negative x and x squared times e to the negative x squared, they look similar. The only difference being, actually, I think I have Desmos opened up here. Yeah, I opened up Desmos last night when I was prepping for this, just to show it. Can you see this? X times e to the negative x. Like, they're scaled differently, but if you only look at, so x greater than 0. Oh no. I only care about x. No, I don't want that. I want like such that x is greater than 0. Okay, you don't do that. Okay, doesn't matter. Point is,
curly brackets.
Oh, what do you do? Like this?
You just, yeah, something like that. Maybe.
Okay, cool. Okay, yeah. So here you like, if I like scale this like by, I don't know, 2, no, by like 0.5. You can see that their shapes are like kind of similar. It's going to be a different graph, but their idea is the same. Like close enough. The shape is like it's a bump and then it goes off like 0 going off. infinity. Like it's still like a bump and then goes down. And the area would tell you the same thing. I'm very vaguely. It's not that chemistry is confusing. It's just that or is that in reference to the image? Okay. Point is, if you convert between these two in some way, shape, or form, you can mark what your activation energy is, how much energy you need to like actually react, what energy particles need to actually be able to react. And then you can compute this area under the curve as it goes to infinity. And then this would be the percentage of particles that are able to react. And all of these other ones wouldn't really be able to react. So only even if you have a mixture at a certain temperature, only a certain portion of these particles will be able to actually do the reaction. Now, important thing to think about is, well, how does this graph change if I increase the temperature of my gas? Turns out, if you increase your temperature of your gas, you'd expect that more particles will have more energy, right? So that means the bulk of the area is going to be like further down the axis, right? But it's still going to have the same like area underneath the curve. And you'd learn how to draw these, but this is like T went up. This like peak shifts further because you have more particles having more energy. Does that make sense why it shifts further? I'll give you a second to think about it. Remember, the area under the curve tells you how many like particles have this much energy. So if you increase temperature, that means more particles have more kinetic energy. And if more particles have more kinetic energy, then this is something else, then you're gonna like there's going to be more area under the curve at higher energies. So like this peak is gonna shift. Yes, no, maybe. And then that's all I'm gonna say. And this, it's not gonna be all I'm gonna say. This kind of explains this part. Well, like it kind of links with this part, because like you need extra energy to give to a particle for it to be able to react, and then lose some of that energy to go back to like normal, to what it's supposed to be. And from this, yeah, what's this? It hurts. And from this, we get that not all particles. This is suppose your activation energy. We get that not all particles will have above activation energy, so not all of them will be able to actually react. Or at least not all of them at once will be able to react. But if we increase the temperature, more particles will be able to react. So this kind of implies that if you increase temperature, reaction goes because more particles are able to react. But that's stuff we're going to be talking about on Wednesday. And my explanation for this is scuffed because I'm like trying to save time. Whew. Any questions about this? Otherwise, I'm done. I hear the clapping very faintly because Zoom is very good at filtering sound.